At the end of this lesson, you are expected to acquire or improve upon your ability to define the four components of an industrial hygiene study and to identify potential hazards in a chemical plant. So, what is industrial hygiene? Industrial hygiene is the science that's devoted to the anticipation, identification, evaluation, and control of occupational conditions that cause sickness and injury. So the four components of an industrial hygiene study has to do with the anticipation, identification, evaluation, and control of these conditions. What we're going to do first is look at what sort of conditions should we be looking to anticipate and identify in a chemical plant. The major hazards in a chemical plant that you should be aware of include toxic exposures, flammable chemicals, reactive chemicals, extreme conditions like extreme temperature, radioactive materials, biohazards, and noise. In the upcoming lessons, we're going to dive a little bit more into how one identifies particular hazards in a process. But first up, we're going to be looking at the evaluation and control of noise hazards as well as thermal radiation. Later on in this course, we're going to spend a lot more time diving into toxic exposure hazards as well as hazards due to reactive chemicals. In this lesson, you were introduced to industrial hygiene and learned the four components of industrial hygiene studies. Those were the identification, anticipation, evaluation, and control of conditions that cause sickness and injury. We also looked at the potential hazards in the chemical plant: toxic exposures, reactive chemicals, noise, biohazards, extreme conditions, flammable chemicals, and such. Coming up, we're going to look more at noise and thermal radiation. Welcome to this first module on anticipating, identifying, and evaluating chemical process hazards. We're going to begin this course by looking at a runaway reaction incident that occurred in December 2007 at T2 Laboratories in Jacksonville, Florida. 4 individuals were killed and 13 others were injured when a 2,500-gallon reactor exploded with a force equivalent to 1,400 pounds of TNT, spreading debris up to 1 mile away from the plant. The owners of this process had degrees in chemistry and chemical engineering, yet were unaware of the runaway reaction hazard and its potential consequences. In response to this incident, the U.S. Chemical Safety Board advised ABET, the Accreditation Board for Engineering and Technology, to work with the American Institute of Chemical Engineers to add reactive hazard awareness to baccalaureate chemical engineering curricula requirements. In this module, after reflecting on the T2 Laboratories incident and the importance of understanding chemical hazards, you'll be introduced to the science of industrial health and hygiene. You will learn about the globally harmonized system, a common language for communicating about hazards, and how those hazards are communicated on safety data sheets, chemical labels, and on the National Fire Protection Association diamond. This will give us a good foundation to delve more deeply into toxicology and reactive chemical hazards later in the course. While most of the course will focus on toxic and reactive chemical hazards, in this module you will also be introduced to noise and thermal radiation hazards, 2 other important occupational hazards. I hope you're excited to get started. Let's jump in. The learning objectives for this lesson are that you are expected to acquire or improve upon the ability to identify the components of the National Fire Protection Association, or NFPA, diamond, and to use the NFPA diamond in order to identify specific material hazards and understand the potential severity of the hazard. A couple important reminders before jumping into the NFPA diamond. Industrial hygiene, recall, is the science devoted to the anticipation, identification, evaluation, and control of occupational conditions that cause sickness and injury. The Globally Harmonized System, or GHS, is an international system created for the unified development of safety data sheets and for unified label development for substances and mixtures. So again, the point is that we need to be speaking the same language when it comes to understanding hazards. And the NFPA diamond will be another mechanism by which you can communicate about material hazards. So with that, let's get to the National Fire Protection Association, or NFPA diamond. The NFPA diamond has 4 quadrants. The blue quadrant communicates the health hazard associated with that material and can receive a numerical value between 0 and 4. A 4 would indicate that this is a deadly substance. 3 would indicate extreme danger. 2 indicates a hazardous material. 1 indicates that the material is slightly hazardous. And 0 indicates that this is a normal or non-hazardous material. The red quadrant has to do with the flash point of the material. Again, this can have a numerical value between 0 and 4, with 4 indicating a material with a flash point below 73 degrees Fahrenheit, 3 being a material with a flash point below 100 degrees Fahrenheit, 2 being a material with a flash point below 200 degrees Fahrenheit, 1 being a material with a flash point above 200 degrees Fahrenheit, and 0 indicating a material that will not burn. The yellow quadrant indicates the reactivity of the material. Again, there can be a numerical value between 0 and 4. 4 means that the material may detonate. 3 indicates that shock and heat may detonate the material. 2 indicates a potential for a violent chemical change. 1 indicates the material is unstable when heated. And finally, 0 indicates the material is stable. Last but not least, the white quadrant indicates any special hazards associated with a material. And instead of a numerical value, here we have labels that indicate the specific hazard. So for instance, acid, or ACID, indicates that this is an acid. ALK indicates that the material is alkali. COR would indicate a corrosive material. OX would indicate an oxidizer. We could have the icon for a radioactive material, or we could see a W, which means that you should use no water with this material. And there could be other icons or acronyms that indicate other potential specific hazards. So this is the NFPA diamond and its 4 quadrants. Let's look at a couple of examples of how we could use the NFPA diamond to communicate about particular material hazards. So our first example, we're going to look at gasoline. So we see that gasoline has a 3 in the red region, which indicates the flash point. That again is a material that has a flash point below 100 degrees Fahrenheit. We have a 1 in the blue quadrant, which indicates a health hazard, and this would indicate a slightly hazardous material. And 0 in the yellow quadrant, which is the reactivity, which indicates a stable substance. And so we have these indications because gasoline, right, can be ignited under almost all ambient temperature conditions. The 1 for the slight health hazard indicates that gasoline can cause significant irritation, and the 0 indicates that we have a normally stable material even under fire conditions. So that would be the NFPA diamond for gasoline. Another example, let's look at the diamond for ammonium nitrate. So here we see a 0 in the red quadrant, which is for the flash point, so that indicates a material that will not burn. We see a 0 in the blue, which is the health quadrant, which indicates that we have a normal or non-hazardous material. We have a 3 in the yellow quadrant, so that indicates that shock and heat may detonate this material, and we see under the special hazards that this is an oxidizer. So again, here, right, we have a material that is capable of detonation or explosive decomposition or an explosive reaction, right, but does require a strong initiating source or must be heated under confinement. So that's where we have the yellow 3 that indicates the severity of this particular hazard. And again, the OX in the white region indicates that this is an oxidizer. This particular information was sourced from the National Oceanic and Atmospheric Administration, or NOAA. So again, here we have a couple of examples of how the NFPA diamond can be read and indicates the particular hazards of these 2 substances. So now that we've reached the end of the lesson, you are expected to acquire or improve upon the ability to identify the components of the National Fire Protection Association diamond. So hopefully now you better understand those four quadrants and what they mean. And we used the NFPA diamond to understand specific material hazards and understand the potential severity of a hazard involving those substances. At the end of this lesson, you are expected to acquire or improve upon the ability to utilize the Globally Harmonized System, or GHS, for safety data sheets and labels. So we saw previously that industrial hygiene is the science devoted to the anticipation, identification, evaluation, and control of occupational conditions that cause sickness and injury. In this lesson, we're going to focus on the identification of some of those conditions. So to that end, the Globally Harmonized System, or GHS, is an international system that was created for the unified development of safety data sheets and for the unified development of labels for substances and mixtures. So the idea is that we need to be speaking the same language when it comes to understanding hazards associated with materials. The link provided here will give you all the information you need to know about the GHS. And in this lesson, we're going to focus on some very important components of the GHS, that being safety data sheets and chemical labels. Safety data sheets have 16 required components, which we can see here in this slide. The first 8 of these components contain general information about the chemical. This general information includes first the identification of the product, who manufactures it, where the manufacturer is located, important phone numbers, how the material is recommended to be used, and particular restrictions on its use. There's then an identification of the hazard. So right up front in the document, what are the hazards regarding this material and particular components of the chemical label, including the pictograms, which we will see very shortly in this presentation. Then we have information on the chemical ingredients and any trade secret claims. First aid measures, so important symptoms to look out for and required treatment if an individual is exposed to the material. Firefighting measures, so how to extinguish the material if there's a chemical fire. Information on emergency procedures in the case of an accidental relief, what sort of protective equipment is needed, and what the proper method is for containing and cleaning up the material. Then any precautions for safe handling and storage of the material, including any incompatibilities with other materials. And finally, information on the exposure control and personal protection. So this would include things like OSHA's permissible exposure limits, threshold limit values, personal protective equipment, and any engineering controls that are needed. Sections 9 through 11, as well as section 16, contain other technical and scientific information about the material. So for instance, we have information on the chemical characteristics of the material, its chemical stability and the possibility of hazardous reactions, and particular information on routes of exposure, related symptoms, acute and chronic effects, and numerical measures of toxicity. Other information on the material is included in section 16 as needed. The final 4 sections in the safety data sheet, sections 12 through 15, are included to be consistent with GHS standards. These include ecological information like ecotoxicity, persistence and degradability of the material, and the potential for the material to be bioaccumulative and mobile in soil. Particular disposal considerations include descriptions of waste residues and information on the safe handling and methods of disposal of the material, and it also includes information on the disposal of contaminated packaging. Transportation information would include the proper name for a shipment, transport hazard classes, packaging groups, and environmental hazards associated with the material. And finally, section 15 describes any safety, health, and environmental regulations that are specific for the product. Before turning our attention to chemical labels, we're going to look at some of the pictograms published by the globally harmonized system that communicate particular hazards of materials. So we're going to look at 9 pictograms. This one indicates a health hazard. This pictogram indicates that we have a flammable material. We have a pictogram for a compressed gas. We have one for a corrosive material. We have one that indicates an explosive material risk. We have one for oxidizers. This pictogram represents environmental hazard. This pictogram represents acute toxicity. And finally, we have a pictogram that represents other hazards that do not fall into one of these other categories. Let's now look at a chemical label and its required components. So there's 6 required components on this chemical label, the first of which is the product identifier. So here we see the product code and the product name. We then have information on the supplier, so the name of the company, the address, and the emergency contact number. Then there's a signal word, and the signal word could read warning or danger. So a warning would be a chemical or product that would present a lesser but still harmful degree of hazard, whereas danger, as we see here on this label, shows that we have a chemical or product that presents a great danger, often an immediate hazard to the person that's handling the chemical. So if any of the hazards associated with this product would indicate a danger, that would outrank warning for any particular hazard. So here we see the signal word, which is danger. The fourth component we see are pictograms. These hazard pictograms we looked at on the previous slide that indicate particular hazards associated with this material. So here we see the pictogram for the health hazard as well as flammability. So we have a flammable chemical. This signal word and this danger then can map to these hazard statements. So the hazard statements are now the 5th required component. And here we have a statement that we have a highly flammable liquid and vapor, and that this material may cause liver and kidney damage. So again, those mapped to those 2 pictograms we saw up higher on the chemical label. The final required component here are the precautionary statements. So we see things here about how to store the material. So it says that we need to keep the container tightly closed and to store in a cool, well-ventilated, locked place. We need to keep it away from heat and sparks and open flame because it's flammable. So we see a number of these information about storage. We also see things about grounding and bonding the container so we don't introduce an ignition source via static electricity. We also see things about not breathing the vapors, wearing particular PPE like gloves, not smoking, eating, and drinking, washing hands, and how to dispose with respect to the regulations in the area. We also see instructions for what to do in the case of fire and also particular first aid instructions. So again, here we see these 6 required components: the product identifier, supplier information, the signal word, the hazard pictograms, the hazard statements, and the precautionary statements. So in this lesson, you are expected to acquire or improve upon the ability to utilize the Globally Harmonized System, or GHS, for safety data sheets and chemical labels. Up next, we're going to look at the National Fire Protection Association, or NFPA, Diamond. At the end of this lesson, you are expected to acquire or improve upon the ability to evaluate exposures to noise and thermal radiation. Previously, we saw that industrial hygiene is the science devoted to the anticipation, identification, evaluation, and control of occupational conditions that cause sickness and injury. In this lesson, we're going to consider noise and thermal radiation as specific conditions that can cause sickness and injury, and we're going to look at methods for evaluating those hazards. When we're talking about injuries due to thermal radiation exposure, we're talking about burns. First-degree burns are superficial injuries. Here, only the top layer of the skin, or the dermis, is damaged. These burns typically appear pink or red in color. Typically, the skin is dry and there might be some slight swelling. These burns can range from tender to extremely painful. A more serious injury would be a second-degree burn. Here, both layers of the skin, the dermis and the epidermis, are damaged. These burns typically appear raw and red, and the skin is moist. There could be blisters that contain clear fluid. These burns generally range from severely to extremely painful. Of course, there are also third-degree burns where the full thickness of the skin is damaged, including the tissues under the skin. We can quantify exposure to thermal radiation as a energy measurement per unit area. So in this table, we see thermal radiation intensity described as kilowatts per meter squared. And what we see is how as the thermal radiation intensity increases from 1 kilowatt per square meter to 12 kilowatts per square meter, how the time for the individual to experience severe pain decreases. So we see 115 seconds for an individual to feel severe pain, so about 2 minutes, right, for a thermal radiation intensity of 1 kilowatt per square meter. And as that increases down to 12 kilowatts per square meter, we see that time to severe pain decreases to 4 seconds, so very quick. We also see the trend for second-degree burns. So for that 1 kilowatt per square meter, we see it would take 663 seconds to experience that to second-degree burn, right? So here we're looking at something in the order of about 11 minutes, and that goes down to 11 seconds as we move towards a thermal radiation intensity of 12 kilowatts per square meter. You can also understand these thermal radiation intensities a little bit better by looking at the effects of some of these. So some of the values you saw in the previous chart were 4 kilowatts per square meter and 12, and so at 4 kilowatts per square meter, a physical effect we would see is glass being ruined. At 12 kilowatts per square meter, we see plastic melting, and going even higher, we see at 15 kilowatts per square meter, we see wood firing. Around 18 to 20, we see destruction of thermal insulation. At 25 kilowatts per square meter, we see the automatic firing of wood. At 37.5 kilowatts per square meter, so here again, thinking of the previous table, here we have an incredibly quick amount of time to pain and second-degree burns. We see damage to process equipment, and at 100 kilowatts per square meter, we see the damage and breaking of steel. So let's go ahead and apply this information in an example so that we can better understand how to evaluate this particular hazard. So we're going to be looking at a flare. And one design criterion for a flare is that the thermal radiation intensity in the vicinity of the flare on the ground, so again, speaking of the impact on workers, should not exceed 1,500 BTU per hour foot squared. The question is, what thermal effect would this have on the workers? So previously we looked at thermal radiation intensity in kilowatts per square meter. So we could convert this 1,500 BTU per hour square foot to kilowatts per square meter. So we can do some unit conversions. The first here would be our conversion from BTU per hour to another energy unit, which would be kilowatts. So we see the unit conversion here. We also then need to convert from square feet to square meters, and we see that 1,500 BTU per hour square foot is equivalent to 4.73 kilowatts per square meter. So looking at our chart, what we see is we are between 4 and 5, closer to 5 kilowatts per square meter. So we see, and we could interpolate here between the plot, but we see that the effect on the worker is that we'd have a time to severe pain for our workers in the vicinity that would be between 18 and 13 seconds, and the time to second-degree burns would be between 57 to 40 degree seconds. So there's still, we wouldn't want people hanging around, too long in that area on the ground in close proximity to the flare while the flare is going. So here's how we see how we could look at, again, this design criterion to understand its impact on our workers. So moving on to considering noise as a hazard, let's look at the noise intensity for a number of different common noisy situations that we might be familiar with. So here we look at noise intensity expressed in decibels. That's what dB stands for. And we see that whispering would have a noise intensity of 20 decibels. A noisy office would have a noise intensity of 80 decibels. A passing truck would be 100 decibels, and riveting at 120 decibels. So we can think about these and compare that to an exposure limit. And so we'll talk more about exposure limits in our next module. But the PEL, which stands for permissible exposure limit, and so that's what a worker could be exposed to consistently for 8 hours a day over a long period of time, that permissible exposure limit is 90 decibels. So here, kind of between the noisy office and passing of a truck. In an environment where employees are exposed to a noise intensity above that PEL, what can be done? Well, here's where control measures such as hearing protection, and we see various types of hearing protection shown in this figure worn by these employees. Hearing protection can be employed to reduce the noise intensity experienced by employees to something below that permissible exposure limit threshold. In this lesson, we learned about how to evaluate exposures to noise and thermal radiation. In the next lesson, we're going to look at the Globally Harmonized System, or GHS. At the end of this lesson, you are expected to acquire or improve upon the ability to identify processes and situations where reactive chemical hazards are likely to be present, and to locate important reference materials for the study of chemical process safety. Hopefully by now you've had a chance to review the Chemical Safety Board video about the incident that occurred at T2 Laboratories in December of 2007. 4 deaths and 13 injuries occurred due to a runaway chemical reaction and large explosion. Due to this incident and their investigation, the Chemical Safety Board recommended to the American Institute of Chemical Engineers, or AICHE, to work to incorporate education about reactive chemical hazards in the college-level chemical engineering curricula. This incident occurred during the production of methyl cyclopentadienyl manganese tricarbonyl, or MCMT, which is a gasoline additive. In the reaction step, the first reaction step, the reaction mixture was heated using hot oil, and once the temperature reached a certain threshold, the temperature was to be controlled using a cooling jacket, which was supplied by a 2-inch city water line. Now, the reaction was scaled up directly from the 1-liter batch size to production size, so the challenges that occurred due to heat management and the difference in the surface area to volume ratio were not completely understood. Now, when pressure would build up and get too high in the system, there was a pressure control valve that could vent hydrogen via a 1-inch pipe, and there's also a rupture disc in place to also vent through a 4-inch vent pipe. The CSB concluded that T2 Labs was unaware of the consequences of the runaway reaction risk, since this pressure release system was not able to effectively reduce the pressure in the vessel in the case of the runaway reaction where cooling was lost and the temperature was rising uncontrollably, and also the magnitude of the energy release and potential consequences were also not well understood. So, outside of the obvious, why is it important to understand chemical reactivity hazards? Well, as we saw with the T2 lab incident, reactions can be violent. They can release large quantities of energy and possibly large amounts of toxic, corrosive, or flammable chemicals. If the reaction is confined, like it was in the T2 Labs incident, the pressure in the container may quickly exceed the capability of the container, which creates an explosion risk. Now, reactivity hazards can be found in particular steps where we're intentionally carrying out chemical operations, so in reactors and chemical processes. So we expect reactions to be there, but they can also occur in some places where we may not expect them, like in mixing or physical processing, like blending and crushing, or also in storage, handling, and repackaging as examples. In this course, focusing on chemical hazards, we'll spend this first week working to anticipate, identify, and evaluate chemical hazards. You'll learn about the globally harmonized system, the National Fire Protection Association diamond, and noise and thermal radiation as hazards. In the second week, we'll dig deeper into toxicology. You'll learn about exposure limits and how to visualize data using dose and response curves, how to fit these models, and make predictions. In the third week of the class, you're going to learn more about reactive chemical hazards. You learn about chemical compatibility and incompatibility, as well as how to characterize chemical reactions using calorimetry. Finally, in the fourth week, you learn about pressure relief. You'll look into pressure protection, different sorts of relief devices, how to handle relief effluent, and you'll learn the general process for designing relief systems. There are a few important reference materials that help shape the content of this course and that I highly recommend in your study of chemical process safety. The first is the textbook Chemical Process Safety Fundamentals with Applications, written by Crowell and Luvar. There's also What Went Wrong by Trevor Kletz and Paul Amiot, and the Introduction to Process Safety for Undergraduates and Engineers, published by the Center for Chemical Process Safety, or CCPS. In this lesson, we looked at identifying processes and situations where reactive chemical hazards are likely to be present. So again, in intentional chemical reaction steps and also in other places where you may not expect them, like in mixing or physical processing, or in storage and handling and packaging. We also looked at important reference materials for the study of chemical process safety and what we'll be covering in this class. Up next, in the next lesson, we're going to be looking at industrial health and hygiene studies. In this lesson, you are expected to acquire or improve upon the ability to describe effects of toxicants, including response versus dose, and use probit equations to quantify the relationship between response and dose. Before we look at how response varies with dose, we first need to look at how we expect the response to a certain exposure to differ within a population. So we know that there are many differences in the population, people's general health, their age, their sex, their weight, as examples. And an important assumption that we're going to make is that the biological response to an exposure follows a normal distribution, which is what we visualize here in this slide. The equation for normal distribution is that f of x, that is our percentage or fraction of individuals impacted, is going to be equal to 1 divided by the square root of 2 times pi times sigma squared. Sigma squared is called our variance, times the exponential function to the negative 1/2 times x. X in this case is our mean response, minus mu. Mu is the mean, and sigma, again here, this is the standard deviation, with sigma squared being the variance. So this is the function of this gold line that we see plotted here. When we assume a normal distribution around a mean of 0, what we're saying is that within one standard deviation, we expect 34.1% of the population to fall into the response that differs between the mean response 0 and 1 standard deviation away from the mean. And we see the mirror image of this on the other side of the curve. So another 34.1% of the population is expected to have a response between the mean and negative 1 standard deviation away from the mean. We're looking further out, we can look at 2 standard deviations. So whereas the total within that first standard deviation is about 68.27%, looking at between 1 and 2 standard deviations on the positive and the negative side of the mean, we see another 13.6% of the population falls into that category. So in total, looking plus or minus 2 standard deviations away from the mean response, another 95.45% of the population falls into that category, so a vast majority of the population. Continuing to look further out to 3 standard deviations, so getting much further away from that mean or average response, we see another 2.1% falls between 2 sigma and 3 sigma. Again, that's another standard deviation away from the mean. Here, from same between -2 sigma and -3 sigma. So totaling now plus or minus 3 standard deviations away from the mean, we have now almost all of our population, 99.73%. So again, we're assuming a normal distribution in responses. So there's going to be some average response in the population, but there's going to be variability in the responses of the population. And the extent of that variability is going to be defined by this parameter, the standard deviation, or sigma squared being the variance. Continuing in our discussion of normal distributions and visualizing the impact on this relationship between the response and the percentage of individuals in the population that have that response, let's look a little bit more about the impact of the two parameters here in our distribution, and that is the mean, mu, and the standard deviation, sigma. So here we have a representation of the distribution you saw on the first slide with a mean of 0. So we see the mean here at 0, and the standard deviation here we're setting equal to 1. So here 1 would be 1 standard deviation, 3 would be 3 standard deviations. So as we saw between 3 standard deviations and -3 standard deviations, plus or minus 3 standard deviations, we see almost all of the population falls into this category of responses. So what happens to this distribution when these parameters change and we either see a change in the mean or a change in sigma? So first, let's look at, again, a mean of 0. So we see on this new blue peak, the mean of this distribution is the same as for the gold peak, but we have a much smaller standard deviation. So this parameter, again, that describes the variability in the population has been reduced. So we still have the same results as we saw on the first slide, where if I look at plus or minus 1 standard deviation, I would have about 68.27% of the population. Plus or minus 3 standard deviations would be 99.7% of the population. But the curve, because of that, because the standard deviation is smaller, right, we see the visual here of a much tighter curve. So if we have a response in the population that has less variability, this would be an example of a distribution that could describe it, where that standard deviation is much, much smaller. Let's look at the opposite scenario where, again, the mean is 0, but my standard deviation is much larger, in this case 2.236. So I see here a much broader curve, right? And again, same rules apply for normal distribution. If I look at plus or minus 1 standard deviation, so if I were to draw a line at, say, about 2.2, so let's say that looks to be, very approximately about here, and over on this side, about here, right? I know that between plus and minus 1 standard deviation, which is 2.236, I have about 68.3% of my population. And so if I had a widely variable response to an exposure, my standard deviation for that distribution would be defined as a much larger magnitude. Finally, let's look at a shift in the mean. So here we have a mean of -2 and a standard deviation of 0.707. And so now we see the mean here at about -2. And just to trace that down very approximately, we're about -2. And again, the curve is defined as so, where if we have plus or minus 0.707, we have 68.3. We can look at 3 standard deviations out to represent a certain percentage of our population. So hopefully we feel reasonably comfortable with normal distributions. What we see is how these parameters, the mean and the standard deviation, influences our model. Right, what we're looking to do is fit a model that represents our population. So we would fit the mean and the standard deviation to the particular responses that we see in our population. Finally, just one more note on this. For a normal distribution, the area under all of these curves is equal to 1. That's important because that would add up essentially to 100% of our population. So now let's look at a response versus dose curve, where we look at The responses on the y-axis will continue to represent those as percentage of the population and how that varies at different doses of the toxicant. Notice also that on the x-axis we have the logarithm of the dose. So the doses could vary widely, so having the logarithm will help us represent this data a little better. What we're looking at now is just a collection of data points that could represent this relationship. And so you might ask yourself, from before, where is the normal distribution here? So for each of these data points, the point here represents the mean response at that particular dose, or plotted on this axis, the logarithm of the dose. And these error bars also have some meaning. Now, that could differ depending on the resource you're looking at. Very typically, the error bars represent plus or minus, so plus on the top and minus on the bottom, the standard deviation. So again, remember the parameters for that distribution are the mean, mu, and the standard deviation, sigma. So each of these points here represents that distribution at that dose, and we map that to their distribution of responses. We see the mean response as well as the sigma that defines the variability in that response. So this shows how this relationship could look, and one thing to notice if we were to put a line through that relationship, and again understand that at 0 dose we'd have 0% of the population responding, and as we approach higher and higher doses we get 100% of a response, of a toxic response to that chemical. Right, what we see here is something that is not linear. We see this sigmoidal relationship between the logarithm of the dose and the response that is described in percentage form. Resetting this for a moment, we can look at different dose curves depending on the particular response that we're interested in. So one such curve could be called the effective dose curve. So we're looking at that a non-lethal particular effect of that dose. So maybe it could be irritation as an example. And what we can describe this relationship in a few different ways. Some ways to do it would be to look at the effective dose where we have a mean response of 10%. So we could say ED for effective dose, subscript 10 for 10%. Another common way to describe this would be where we have 50% of the population responding. So this point right here, this dose corresponding to this point, could be described as the ED50. Another dose curve we could be looking at is a toxic dose. So toxic dose, abbreviated TD, where we have some toxic effect on the individual. Again, we see this plotted on the logarithm of the dose versus percentage of responses. And similar to the effective dose curve, we could describe this using something like the TD50, or the toxic dose, where 50% of the population responds in that way. Finally, another curve we could show is the lethal dose curve. So of course here the response we're looking at is death in the population. And so again, another common way to quantify that would be looking at the LD50, or the lethal dose for 50% of the population. Going back to our original logarithm of dose versus percentage response curve, we now see that if we had some data, what we could like to do with that is fit this trend. So say at the 50% mark, we could make a prediction. Say here would be the place where we have either the ED50 or the LD50, depending on if this is an effective dose curve or a lethal dose curve. And so we like a way to fit this response curve based on the data. The trouble is that with this nonlinear relationship we see between the logarithm of the dose and the percentage of responses, this is a difficult thing. It's not very convenient. And the easiest way to fit a relationship, the easiest model we can think of, would be that of a line. So another way of saying this is we'd like a way to linearize this data such that we can fit a line to a dose versus response relationship. And a way that we could do that is by converting our response in percentages to a response in something called probits. So we want to transform percentages into probits. And what we like that to be able to do is convert this gold, nonlinear, more sigmoidal curve into a line. And if we can fit that line, we can have a linear relationship that we can very easily quantify. And then we could go about converting that back to percentages. So how does all of that work? Well, first, here is the function for that probit transformation. So here, this P represents percentage, and Y over here, this is the probit. So it's a pretty complicated relationship, right? We see that the percentage is equal to 1 over 2 pi. We have the integral from negative infinity to y minus 5 of e to the negative u squared over 2 du. The visualization for that function looks like this. And so just a couple of things just to point out from this relationship. We see that the point at a 50%, that is equivalent to the probit value of 5. We see that as we approach 100%, the probit value comes up to 8. And on the other side, as we approach 0%, the probit value goes down to 2. So we also see that this more sigmoidal, there's a mirror image here, on this point here where we have 50% and 5 probits. We see kind of the same sort of nature of the relationship inverted on both sides of this inflection point. And there are tables that can help you move from percentages to probits. If you're in Microsoft Excel, you can make this calculation if you have probits. So if you have Y, you can make a calculation for the P percentage using this function. So we have 50 times inside the brackets 1 plus y, y is what's probits, minus 5 over the absolute value of y minus 5 times ERF. This is the error function, ERF. The argument to the error function is the absolute value of y minus 5 over the square root of 2. So again, pretty complicated transformation here. And in the next video, we'll go through an example and demonstrate really how to work all this. Again, the goal here is if we move from percentages to probits and get a linear relationship, what we can do is then fit a line to the y in probits as a function of the natural log of the causative variable. So here's the causative variable. Often case for our applications, this is the dose. So as we saw, if we have on the x-axis the natural log of the dose, which is this right here, and the y-axis we have probits, y, and we have a linear relationship in that data, we can fit the slope, k2, and the intercept, k1, and we can quantify this relationship. So that may all seem a little bit abstract right now. Again, stay tuned. What we're going to do is we're going to walk through an entire example of some dose versus response data, visualizing that, converting that to probits, quantifying the relationship, and looking at how we can use that to quantitatively fit and describe this relationship between dose and response. In this lesson, we learned about the effects of toxicants and visualized them using response versus dose curves. We also looked at how we can use a probit transformation in order to quantify the relationship between response and dose by converting it to a linear relationship. In the next lesson, we're going to demonstrate this whole process using an example. The learning objectives for this lesson is that you're expected to acquire or improve upon the ability to define, discuss, and utilize exposure limits, such as the threshold limit value and permissible exposure limit, and understand relative toxicity and its importance. So now that we better understand dose versus response and how to model that, how can we go about describing and communicating toxic concentrations of chemicals? One such means would be the threshold limit value, or the TLV. The TLV is the maximum exposure limit to humans for 8 hours a day and 40 hours a week over a long period of time that does not cause any noticeable effect. So here, what we're looking at is a normal worker's lifetime. TLVs are promulgated by the American Conference of Governmental Industrial Hygienists, which is a professional society, and these do not carry legal authority. Another way to describe these concentrations is the permissible exposure limit, which is essentially the same thing as the TLV. They are not as numerous and they are not updated as frequently. However, because they are promulgated by OSHA, which is a governmental organization in the United States, the PLVs would carry legal authority in the US. The TLVs, or the threshold limit values, can be further broken down. So this first version of the TLV, the time-weighted average, is as was described on the previous slide. We're looking at a concentration that one could be exposed to for 8 hours a day, 40 hours a week, and not suffer any adverse effects. A short-term exposure limit, so the TLV-STEL short-term exposure limit, this is a higher concentration that is believed a worker could be exposed to a short period of time and not suffer any adverse effects. And so this short period of time is commonly defined to as about 15 minutes, and that 15-minute exposure should not occur more than 4 times a day, and there should be at least 60 minutes between successive exposures at the TLV-STEL. Finally, the ceiling, the TLV-C, this is a concentration that should not be exceeded at any point during the worker exposure. So here are a few examples of TLVs for ammonia and for formic acid and methyl acetate and methyl isocyanate, which was the chemical involved in the Bhopal release. So a few observations, right? We see the concentrations here are all expressed in parts per million. We see again that, let's look at ammonia where we have the most information. The time-weighted average, this 8 hours a day, 40 hours a week exposure, that concentration is less than the short-term exposure limit. That's again for a short period of time, about 15 minutes, very few times a day with some time in between. And the ceiling, this is the concentration that workers should be never exceeded for the workers. And we see the comparison here again to the PEL, that is the permissible exposure limit that does carry the weight of law, right? And in this case, the PEL for ammonia is equivalent to the TLV-C, or ceiling. We see other examples for formic acid. The PEL in this case happens to be equivalent to the TLV-TWA. Same is true for methyl acetate, and same is also true for methyl isocyanate. And we don't have, again, TLVs, short-term exposure limits and ceiling reported for all of these different chemicals. One final note on this is that these threshold limit values or permissible exposure limits are not meant to be used as an indication of relative toxicity. And that is to say, for example, looking at, say, formic acid and ammonia, we notice that the time-weighted average TLV for formic acid is less than ammonia. So is it okay to say that formic acid, therefore, is more toxic than ammonia? We need to be careful of that, and let's understand that more here on the next slide. So to understand that better, let's look at two toxicants, A and B, and we're going to look at their dose versus response curve. So we have log dose on the x-axis, and we have the percentage toxic response on the y-axis. So let's say we have these two toxicants. So in green, we have the dose versus response curve for toxicant A, and here in red, we have a different dose versus response curve for toxicant B, and the slope of that response is much more gradual than we see for toxicant A. So again, what we're considering here is why it's important not to make judgments on relative toxicity based on partial information. And so let's look at the toxic response for 10% of the population. And so based on that metric here, looking at the TD10 for toxicant B and the TD10 for toxicant A, right, we see that we achieve that at a lower dose for B than for A. So in this case, it would appear that B would be more toxic than A. However, if we look at the TD50, where 50% of the population is affected, we see that happens at a lower dose for A than it does for toxicant B. So again, we can see that these curves are maybe an intersection of these curves because the slopes are so different. So at lower doses, you might have one toxicant that's more toxic than the other. So again, B was more toxic than A at lower doses, but at higher doses, A is more toxic than B. So again, be careful when making judgments based on toxicity of two or more species based on partial information. In this lesson, we learned about exposure limits, like the threshold limit value, TLV, and the permissible exposure limit, PEL. We learned how TLV can be broken down into the time-weighted average, the short-term exposure limit, and the ceiling. And we looked at some examples for various chemicals. We also looked at relative toxicity and understand why it is important. Coming up, we are going to be looking at control techniques for toxic chemical exposures. At the end of this lesson, you are expected to acquire or improve upon the ability to describe control techniques to prevent toxic chemical exposures. The first control measure we're going to look at is ventilation. Ventilation is the most common method for the control of airborne toxic and flammable materials in an enclosed environment. If designed well, a good ventilation system will dilute a toxicant below a target concentration and remove the toxicant before the workers are exposed to hazardous levels. A ventilation system is composed of fans and vents, and the exhaust system can operate under positive pressure, where air is forced back out into the space through the exhaust, or it could operate under negative pressure, where air is taken back in to the vent and then exhausted. So for the control of concentrations of toxic or flammable materials, the exhaust system should work under negative pressure. Let's now look at a few other important examples of control measures in the workplace for the prevention and mitigation of toxic chemical exposures and other hazards. A first example for the prevention of exposures would be enclosures for hazardous operations. So here as an example, we see a chemical fume hood, which could enclose a hazardous process. It would also include ventilation, as we discussed in the previous slide, for the removal of toxic or hazardous vapors. Chemical storage cabinets can be used to separately store things like acids or bases or flammables, such that things like acids and bases wouldn't interact and react, producing a chemical reaction which could have hazardous consequences. Similarly, a place to keep flammables such that we can prevent exposure to ignition sources. In the mitigation realm, we could have things like safety showers and eye wash stations to dilute and remove chemicals from an individual's skin or clothing. Spill containment to contain a spill in a smaller location or footprint before it is more widely distributed in the environment. Emergency notifications are things like beacons and alarms to alert individuals of the presence of a toxic chemical. And of course, the emergency response to a particular incident. Important last line of defense control measures are personal protective equipment, or PPE. PPE are barriers between the worker and the workplace environment. Different jobs will require different PPE, so it's important to have the right personal protective equipment for the job. Different types of PPE include head protection, like safety helmets, Eye protection like safety glasses or goggles or screens or shields. Breathing apparatus, this can include a full face mask or disposable masks. Ear protections, these could be earplugs or ear muffs. Gloves. Fall arrest like harnesses or ropes. Different clothing options like flame resistant clothing. And footwear like safety boots. In this lesson, we learned about control techniques to prevent toxic chemical exposures. Coming up next, we're going to be learning from important historical case studies. Welcome to this next module. We will turn our attention to the study of toxicology. Toxicology is the field of science that helps us understand the harmful effects that chemicals and substances can have on people, animals, and the environment. Toward the end of this module, you will reflect on two different incidents that resulted in worker fatalities due to toxic chemical exposures. These incidents occurred in November 2014 at DuPont's La Porte facility, where 4 workers were killed after being exposed to a toxic concentration of methyl mercaptan, and in October of 2019 when a worker and his wife were killed after being exposed to hydrogen sulfide gas at the Aghorn Operating Water Flood Station in Odessa, Texas. These incidents speak to the importance of understanding and properly managing toxic chemical hazards. After completing this module, you will better understand how to describe chemical toxicity using exposure limits, such as the permissible exposure limit and threshold limit values. You'll be able to define how toxicants enter the body and why the exposure route is important. You'll be able to formulate dose versus response curves and use them to make predictions about the impact a toxicant will have on a group or population. And finally, you will be able to describe important control measures for mitigating the impact of toxic chemical hazards. I hope you're excited to get started. Let's jump in. At the end of this lesson, you are expected to acquire or improve upon the ability to define toxic hazard and to explain how toxicants enter and are eliminated from the body. In the first week of this course, we saw that toxic hazards can be one of the most important hazards one faces in a chemical process. So how can we more specifically define toxic hazards? They can be defined as the danger posed to living organisms by a toxic agent. This danger involves two things. First is the toxicity of the agent. We can describe the toxicity of the agent as the quality, state, or degree to which a substance is poisonous and or may chemically produce an injurious or deadly effect. The second component would be the means by which it's introduced to the subject organism. So considering the second point, we can ask 3 questions. The first is, what mechanisms can toxic agents enter the body? Why are these different mechanisms important as it relates back to understanding the toxic hazard? And by which means can toxic agents be released or eliminated from the body? So let's consider these 3 questions next. As we explore the different mechanisms by which toxic agents can enter the body, we're going to be looking at the relative blood level of the toxin as a function of the time after administration. When we do this, that will allow us to compare where we see the peak concentration in the toxin as well as the magnitude, how high is the relative blood level. So let's get into this. The first of the mechanisms we're going to be looking at is inhalation. So here we have the toxic agent entering the body by breathing it in through the lungs. So consider again here the path of the toxic agent into the bloodstream. So when it's breathed in, right, there is some delay here until we see the peak in the concentration of the blood. And we also here see the elimination over time of the toxic agent from the body. So this is kind of our first frame of reference here as we look at the relative blood level versus time, and now let's compare it to something else. So a second mechanism would be ingestion. So here we have the toxic agent entering the body through the GI tract. So here for ingestion, we have this green curve. So what we see as compared to inhalation is first a smaller magnitude in the relative blood level, and also a longer time until we see the peak concentration in the blood in this curve. So again, consider the different barriers here the toxic agent has in getting into the bloodstream through the GI tract. A third mechanism is absorption. So here we have the toxic agent entering the body through the skin. So the skin is obviously one of the key barriers protecting our body. So here, when we look at absorption through the skin, we see much lower relative blood levels of the toxin, and again, an even longer time period till we see the peak concentration in the blood. A final mechanism would be injection. So here we have the toxin being injected directly into the blood. So as you might expect here, we see the highest relative blood levels as compared to inhalation and ingestion and dermal absorption, where we have different barriers between the toxin and the bloodstream. And so we see the highest relative blood levels and a very quick rise to that peak concentration in the blood. So these are the different mechanisms by which a toxic agent can enter in the body. And here, the importance of the mechanism as it relates back to the toxic hazard has to do with first these differences in the concentrations we expect in the blood due to the mechanism by which they enter the body, and the time until we see that max. So we see differences in both regards, again, on the magnitude as well as the time until we see the peak concentration. That's all dependent on the mechanism by which the toxin enters the body. The final thing we wanted to consider was the elimination of toxicants from the body. We see clearly on the charts we have for relative blood level versus time after administration, this decrease in relative blood level of time. So here we see the body working to eliminate the toxicant. So what mechanisms can be used for this? One mechanism would be through excretion. So think bodily excrements, urine, sweat, etc. This can be used in order to remove the toxicant and decrease the concentration of it in the blood. A second mechanism would be through chemical transformation, so through detoxification or biotransformation. So converting that toxicant to something that is less toxic and eliminating it from the body. Finally, the body can store the toxicant in fatty tissue and thereby remove it from the blood. In this lesson, we learned about toxic hazards. We looked at the definition of a toxic hazard and learned that there's two components: the toxicity of the agent and the means by which it is introduced to subject organisms. To that second part, we looked closely at how toxicants can enter the body and how they are eliminated from the body. Coming up, we'll look at dose versus response curves. In this lesson, we're going to look at an example of modeling a dose versus response curve using some real data. So just as a quick reminder, a dose versus response curve is typically first illustrated by looking at the logarithm of the dose versus the response. So here we see this gold curve here with some data points indicating some uncertainty in each of these data points. Modeling such a nonlinear response is tricky, so we can convert this dose response curve into a log dose versus a response and probe it to convert this into a linear relationship to which we can fit a line, which would be a model between dose and response. Here again, we see the transformation from percentages to probits and the function that describes this relationship. We said that for spreadsheets, we can calculate a percentage from probits using this expression, which would make a calculation for the function described on the left. And we're here Y is probit and the P is percentage. When we get a line, we can fit a line, and so we have Y, the probits on the Y-axis, and the natural log of usually dose is the causative variable, but whatever our causative variable is, we can fit a line and quantify that relationship using the slope of the line, which is in this case is K2, and the intercept of the line, which is K1. So let's walk through a real example and see how all of this works. So for our example, we're using the works cited at the bottom of the slide to obtain some data that describes the toxicity of rotenone to the insect species Macrosiphinella sanborni. The rotenone was applied in a medium of 0.5% saponin containing 5% alcohol. So the insects were examined one day after spraying, and the data is as shown. So we have different doses of rotenone in concentrations of milligrams per liter. We have the number of insects that were treated, and we have the number of insects that were adversely affected. So let's go ahead and walk through how we can plot our dose response curve and derive a model that describes quantitatively dose versus response such that we can make predictions. So the first thing we're going to do, and I did all of this work on a Microsoft Excel, so just basic spreadsheeting software, is just to make a data table using the data on the previous slide. So again, we had here 5 different doses of rotenone in milligrams per liter, the number of insects that were treated, and the number of insects that were affected. So to plot my first version dose versus response curve, let's go ahead and calculate the percentage affected. So again, the percentage affected is just the number of insects affected over the total number of insects that were treated. So for example, 44/50 times 100%. And I can plot, again, the dose of rotenone here in milligrams per liter over the percentage of the insects that were affected. And again, I see this relationship here, right? That's a nonlinear relationship where I see some increase in plateau as we get closer to 100%. Next, we're going to want to linearize this relationship by converting this dose versus percent insects affected into a natural log of the dose versus probit. So when we do that, again, we expect to see this nonlinear relationship convert to a linear relationship. So we can populate our data table and get a column for the natural log of the dose. So again, here we're just taking the dose of rotenone and taking the natural log, and so we have one column here. And then we need to calculate or convert from percentage to probit. And so we had a function for converting from probit to percentage, and how do we go kind of the other direction, right? That's obviously a really complicated function. In Microsoft Excel, there is a function that will do that conversion for us. So if we use the norm.s.inv function and take our percentage and divide it by 100, so we want to get out of percentage form, we can take this result of the norm.s.inverse function and add 5, and that will give us our value in probits versus percentage. So just to validate this, when we wrap up this example, I'll show you about going kind of back from probits to percentages so you can be comfortable that this is doing what it's supposed to be doing. But this is a tool in Excel that will convert from percentages into probits, and again, kind of that midpoint for the probit is 5, which is why we have the 5 added here. So when I do that to the percentage affected column, we get this probits column, which is the execution of the function that we see here. If you were to plot the natural log of the dose versus probits, you would get a plot that looks like this. And so these blue dots, again, are the ln dose versus probit. So we're essentially plotting these last 2 columns right here. We see something that looks a lot like a line. So our expectation that this would become a linear relationship makes it, we all see that here. We can fit a line to our data, so we can use the regression tool, in this case in Microsoft Excel or whatever spreadsheeting or programming language you like to use. So fitting a line, we see a line function of y in this case being probits, equals to 1.8154x, x being the natural log of the dose, plus the intercept 2.1305, and the r-squared value showing the goodness of fit is 0.9767. So we see a very strong linear correlation here for natural log of dose versus probits. So to complete this example, let's first transcribe that linear function we just derived. We have the natural log of the dose multiplied by this slope and this intercept of the linear function, and that calculation will give us the percentage response in probits. So again, for any dose I'm looking to make a prediction of response for, I can plug in dose, calculate the response in probits. Now that's great, but probits may not mean a lot to me, or wouldn't mean a lot to me. So I would need a way to convert back out from probits to percentages. And here's where we had this function that was presented where I can calculate the percentage by plugging in y in probits and making this calculation. Again, this invokes the error function ERF, which is a function that I could use in Excel. Alternatively, you could use a function much like the one in Excel that I used to convert from percentages to probits. This function is norm.s.dist. This function takes as the first argument your value in probits minus 5, and the second argument is true. This will give you a value for the percentage in terms of a decimal. To get that to percentage form, you multiply by 100. So this is a table that shows these calculations. So what I did is for a number of natural log of doses, these are natural log of doses, we have a range from 0.5 all the way to 2.5 with an increment of 0.1. We make the calculation for probits. The calculation for probits here is by plugging in the natural log of a dose into this function, multiplying it by the derived slope of the relationship, 1.8154, adding the derived intercept, 2.1305, and we get a result for y, which is probits. So we've done this for a number of natural log of doses. The next column to convert this to percentage, I did it for both functions. It's the same thing. We're plugging in y here either into this function and calculating percentage, or you could do this Excel function and convert from probits to percentages just the same. And so this will give you a percentage impacted at all of these natural logs of the doses. So plotting these things, so first in blue, these blue dots, these are our original data points. So these are the original data points where now I'm plotting the natural log of the dose of rotenone by the percentage affected. In red here, this is the trend line where the linear fit for natural log of dose to probits has been converted to natural log of dose, that's this column, and percentage, this column here. So this red line is this plot of my function that I derived in terms of natural log of dose and percentage. And again, we see that this function fits our data very well. So it's kind of a nice validation for ourselves that we went through this the right way. And again, we see now we can make a quantification or prediction for the percent of insects affected, first in terms of probits, then converting to percentage based on some dose that we're interested in. So I hope this has been a nice illustrative example of applying the tools that we learned for dose and response curves. At the end of this lesson, you are expected to acquire or improve upon the ability to identify processes and situations where reactive chemical hazards are likely to be present. Earlier on in the course, we talked about why it was important to understand chemical reactivity hazards. As a reminder, chemical reactions can be violent. They can release large quantities of energy and possibly large amounts of toxic, corrosive, or flammable materials. If the reaction is confined, the pressure in the vessel may quickly exceed the capability of the container, which of course creates an explosion risk. These chemical reactivity hazards are likely to be found in reactors where you've designed intentional chemical operations, but they could also be found where you have mixing and physical processing, like blending and crushing, as well as where you are storing chemicals or also handling or packaging chemicals. The Crowell-Navarre Chemical Process Safety Fundamentals with Applications textbook provides some important questions that we can ask to discern if reactive chemical hazards can be expected in our process. The particular questions are, is intentional chemistry done at the facility? A follow-up question to this, if the answer is yes, is any chemistry done besides combustion with air? Another question is any mixing or combining of substances done at the facility? Are there any other physical processing steps? Is heat generated during mixing or processing? Are any hazardous substances stored or handled at the facility? And are there any specific reactive hazards? Like, do we have a self-reactive chemical or a chemical that can react with water? And we will go over types of specific reactive hazards in the next lesson. So depending on the answers to these questions, yes or no, that could indicate if we should expect reactive chemical hazards or if reactive chemical hazards are not likely. So what are the combination of yes answers to these questions that would lead us to expect reactive chemical hazards? A first situation where we expect there to be reactive chemical hazards at the facility is if we could answer yes to the question of, is intentional chemistry done at the facility? And also yes to the follow-up question of any chemistry besides combustion with air being carried out at the facility. Now, combustion is also a special reactive hazard, and it's not the focus here as it's handled by separate codes and standards. A second situation where we could expect reactive chemical hazards at our facility is if we could answer yes to the question of any mixing or combining of substances at the facility, and yes to either heat being generated during mixing or processing, or yes to there being any specific reactive hazards associated with the substances that we are mixing or combining. A third situation where we expect there to be reactive chemical hazards present at the facility is if we could answer yes to the question of any other physical processing other than mixing or combining of substances, and also yes to one of these two questions of, is there heat generated during mixing or processing, or again, are there any specific reactive hazards with the substances involved in the physical processing steps? A final situation where we'd expect reactive chemical hazards at the facility is if there are any hazardous substances that are stored and handled. So if we can answer yes to that question, and also answer yes to any specific reactive hazards associated with those substances that are being stored or handled, then again, we'd also expect there to be reactive chemical hazards that must be managed at our facility. In this lesson, we identified processes and situations where reactive chemical hazards are likely to be present. One of the questions we considered was, are there any specific reactive hazards associated with the substances? So in our next lesson, let's talk about what those specific reactive hazards are. At the end of this lesson, you are expected to acquire or improve upon the ability to understand and describe specific reactive hazards. Before we dive into specific reactive hazards, a good place to start to look for these are on material safety data sheets. Here we see an example part of a safety data sheet for acetic anhydride. And we can recall from earlier on in the course that section 2 of the safety data sheet is for hazard identification. Here in section 2.3 of this safety data sheet, we see that acetic anhydride reacts violently with water, which is a reactive chemical hazard. There are 6 specific reactive chemical hazards that you should be familiar with. Spontaneously combustible materials carry a reactive hazard. Spontaneously combustible materials readily react with oxygen in the atmosphere and can ignite and burn even without an ignition source. On the safety data sheet, these materials can be labeled as either spontaneously combustible or pyrophoric. On the National Fire Protection Association diamond, these materials would carry a flammability rating of 4. And an example of such a material is triethyl aluminum. Peroxide-forming materials also present a reactive hazard. Peroxide-forming materials react with oxygen in the atmosphere to form unstable peroxides. An example of such a material is diethyl ether. Water-reactive materials also present a reactive hazard, particularly when they react with water under normal ambient conditions. Usually these materials are labeled as water reactive on safety data sheets, and they may also be labeled as dangerous when wet. There's a special symbol on the National Fire Protection Association diamond for water reactive chemicals. One example of such a material that reacts with water under normal ambient conditions is sodium. Materials that are oxidizers also present reactive hazards. Oxidizers readily yield oxygen or other oxidizing gas, or readily react to promote or initiate combustion of combustible materials. These materials are identified as an oxidizer on safety data sheets, and on the National Fire Protection Association diamond, it carries a special symbol OX for oxidizer. An example of an oxidizer is nitric acid. Self-reactive materials also present a reactive hazard. This is because the reaction often accelerates with dangerous consequences. On safety data sheets, self-reactive materials are often identified as such, as being self-reactive. And on the National Fire Protection Association diamond, these materials should receive a reactivity rating of 1 or higher. These reactions can include polymerization reactions of monomers. So for example, we have styrene highlighted on the slide, which can react to form polystyrene. But it can also include large molecules that thermally decompose into smaller, more stable molecules, or also rearrangement of atoms in a larger molecule to form different molecular structures, such as isomers. A final specific reactive hazard are incompatible materials. Incompatible materials, when coming into contact with each other, will result in a chemical reaction. An example of incompatible materials are acids and bases, which is why these materials should be stored separately. In the previous lesson, you learned about specific reactive hazards, including incompatible materials. In this lesson, you'll learn how to create and use a chemical compatibility matrix using a tool called the Chemical Reactivity Worksheet. The Chemical Reactivity Worksheet is a helpful tool for identifying specific reaction hazards in a process. The tool is developed by the Center for Chemical Process Safety, which is a part of the American Institute of Chemical Engineers, or AICHE, the National Oceanic and Atmospheric Administration, the US EPA, in collaboration with the Dow Chemical Company and the Materials Technology Institute. The reactivity worksheet is available through the AICHE website at the link shown here. And as of the recording of this video, the version that was available is version 4.0.3. We're now going to go through an example of generating a chemical compatibility matrix using this chemical reactivity worksheet. When you download and install the program, you're presented first with a screen called the Mixture Manager. In the Mixture Manager, you can create a new mixture, which I called my mixture, and then you can add particular components to your mixture. So to add components, you can search for chemicals, and you can search using things like the name of the chemical, or the CAS number, or the chemical formula. And you'll see any hits for your search here under chemical name. So I searched for sodium bicarbonate, and I got this one hit. And you can see information on that chemical. You see its name, the CAS number, its chemical formula. You see a general description of the component, different synonyms, and information like that. Once you've found the chemical you're looking for, you can click on Add to Mixture, and it will show up under my mixture below. So I've already added to this mixture acetic acid, ethyl acetate, sodium hydroxide, and water. And once you've added all the components to your mixture that you'd like to, and you want to see the chemical compatibility matrix, you can click on View Chart to generate the matrix. When you click on View Chart, there's a number of different results that come up, but the first thing that might stand out here is the compatibility chart for my mixture. And so you see the 5 components that I defined for my mixture, both here coming down in the rows as well as in the columns. And so we see a result for the binary interaction between each of our components. So for example, with ethyl acetate with acetic acid, and sodium bicarbonate with acetic acid and ethyl acetate, and so on. So what we see here are a number of different icons, when the legend for this is that the green Y represents that we have compatible components, so we don't expect any hazardous reactivity issues. The red N is for incompatible components, where we do expect there to be hazardous reactivity issues. C indicates caution, that there may be hazards under certain conditions, and SR indicates a potentially self-reactive material. If we click on a particular result, so for instance, if we click on the N for the sodium hydroxide solution in the acetic acid solution, we see some more information about the nature of this incompatibility. So this is a box you see with a few tabs. First, looking under the hazard summary, you see for the selected chemical combination how we have the potential for corrosive reaction products and flammable reaction products, that the reaction between these two components liberates gaseous products which could cause pressurization, that under ambient conditions this is an exothermic reaction that releases heat, that the reaction can be particularly intense, violent, or explosive, and that the reaction products may be toxic. Also, on this, when looking at these different matches, you see intrinsic hazards of all the different components. So in this particular match, we're looking at acetic acid and the sodium hydroxide, but just kind of skimming down the intrinsic chemical hazards, you see, for instance, that ethyl acetate is flammable and it's a peroxidable compound. Exploring one more tab here for the sodium hydroxide and acetic acid combination, you can look at the potential gases that can be created as a result of this reaction between sodium hydroxide and acetic acid. You see that you can have acid fumes, ammonia, base fumes, hydrogen, and oxygen created. So those are just some results generated for that particular interaction, but one last feature just to point out about using this tool, and I highly encourage you to download this and install this and play around with it, is that you can generate a mixture report. So again, for the mixture report, you see all the different components of my mixture, and under the predicted hazards, you can see report outs for each of the different combinations. So if you're here, the ethyl acetate and acetic acid combination, we see the potential hazards, the potential gases that are generated. And so you'll see this as you scroll down for all the interactions. Again, there are a few, like this is the interaction of ethyl acetate with itself, that there are no particular reactions expected. It's not a self-reactive chemical. So you can get a full readout of all these interactions, and you could go ahead and preview and print this report. So this would be a great, very useful tool when you have a list of the components in your process and are interested in looking at the potential for incompatibilities and reactive hazards. Some final important notes on chemical reactive hazards before we leave this identification of hazards discussion and go towards characterizing chemical reactions. As pointed out by the Crowell and Luvar Chemical Process Safety Fundamentals of Applications textbook, are that only 25% of reactive chemical incidents occurred in chemical reactors, where we expect chemical reactions to be happening. And the other 75% occur in piping, where chemical reactions were not expected. 90% of reactive chemical incidents could have been prevented with the application of publicly available information, like the information that was generated using the chemical reactivity worksheet. Thinking about that high percentage of chemical reaction incidents that occurred outside of reactors, a lot is due to accidental mixing, and this is a common problem. Also, process upsets where conditions deviate from the expectation can also lead to reactive chemical incidents. In this lesson, you learned how to create and use a chemical compatibility matrix using the chemical reactivity worksheet available through the AICHE website. Up next, you're going to look at a relevant case study, one that involves reactive chemical hazards, entitled The Dangers of Popcorn Polymer, an Incident at the TPC Group Chemical Plant. In this next series of lessons, you are expected to acquire or improve upon the ability to characterize chemical reactions using calorimetry. Within this overall objective, you will learn about the key results that are needed in calorimetry studies, how lab-scale results can be representative of large commercial reactors, how to obtain calorimetry data, and how to analyze calorimetry data. In this lesson, we'll focus on the key results that are needed and how lab-scale results can be representative of large commercial reactors. As we hopefully learned from the T2 Laboratories incident, it is really important to characterize chemical reactions before performing them at large scale. Particular information is needed to ensure that control and safety systems are in place to prevent runaway reactions and to provide pressure relief and to achieve the design goals of the process. 8 important questions that must be asked are outlined in the Crowell-Navarre Chemical Process Safety Fundamentals with Application textbook. For each of the key questions, the word associated with the result we need is highlighted in red. So let's go through these questions. The first is, at what temperature does the reaction rate become large enough for the adequate energy to be produced for the detection of reaction mixture heating? What is the maximum temperature increase due to adiabatic self-heating of reactants? What is the maximum rate of self-heating, and at what time in temperature does this occur? What is the maximum pressure during the reaction, and is this pressure due to the vapor pressure of the liquid or due to the generation of gaseous reaction products? What is the maximum pressure rate, and at what time and temperature does this occur? Are there any side reactions that occur, particularly at temperatures that are higher than the normal reaction temperature? So again, think about deviant conditions here. If this is the case, can we answer the first 5 questions for these side reactions? Can the heat generation from the desired chemistry heat the reaction mass under adiabatic conditions to a temperature at which another reaction occurs? And can the heat generated by the chemical reaction, whether desired or undesired, exceed the capability of the vessel or process to remove heat? And at what temperature does this occur? So that's a lot of information that we need, and we're going to come to appreciate calorimetry studies as a way that we can answer these questions. But as we build up to that, let's first talk about what the essential features are for an industrial characterization method for chemical reactions. So what we want is a small lab-scale experiment that uses small quantities of materials. In this way, we can ensure safety so that we can manage the hazards associated with the chemistry, and is also simple and low cost. Another essential feature is that the results of the experiment need to be representative of a large commercial reactor. And there are challenges in having a small experiment be representative of what happens at large scale. And one of the primary challenges is that large reactors have a low surface area to volume ratio. So heat removal from the large-scale process will be much more challenging. If we were to look at a sample in a large reactor, that sample, because of this low surface area to volume ratio and how heat is removed at the large scale, that sample is going to be at the same temperature, essentially, as the fluid that surrounds it. What this means is, on the small-scale experiment, we need adiabatic conditions, so heat cannot be entering or leaving our system, in order to be representative of the large-scale process. A final essential feature of an industrial characterization method is that we like to get the results we need, which are in part the answers to the questions that we saw earlier on in this presentation in one experiment. As we move on in this series of lessons, we're going to appreciate calorimetry studies as a way to get these results. In this lesson, we talked about the key results that are needed to characterize chemical reactivity and how lab-scale results can be representative of large commercial reactors. In our next lesson, we'll talk about what calorimetry is and how we can obtain calorimetry data. In this series of lessons, you are expected to acquire or improve upon the ability to characterize chemical reactions using calorimetry. In this particular lesson, you're going to learn about the adiabatic calorimeter and how to obtain calorimetry data. In the last lesson, we talked about some essential features in an industrial characterization method for chemical reactions. We said in part that we're looking for a small lab-scale experiment that uses small quantities of materials. That way we can effectively manage hazards and have a simple, low-cost experiment. We also said that the results needed to be representative of a large commercial reactor. And the particular challenge we said there was that we need to represent adiabatic conditions for our results to be representative of the large-scale reactor. And that, again, was because taking a sample out of a large reactor, the sample is at about the same temperature as the fluid surrounds it, because large reactors have a low surface area to volume ratio. So it's more challenging to remove heat from the large-scale system. So how does a adiabatic calorimeter allow us to meet these essential features of an industrial characterization method? The adiabatic calorimeter, as the name suggests, is configured to keep the external temperature the same as the reaction sample temperature. There are many types of calorimeters, and here we see a general picture of what a calorimeter is. We have an insulated container inside of which we have a reaction sample cell. There are two thermocouples, one that measures the temperature inside the sample cell and one that measures the external temperature, and we have a heating element that is connected along with the thermocouples to a control box. We need a control system that can very quickly respond to high self-heating rates of the sample in an attempt to keep the external temperature the same as the temperature of the reaction sample. We also need a thin-walled sample cell to reduce the heat absorbed by the sample cell walls. Most calorimeters have two modes of operation, and the most common of these is called thermal scan mode. The figure here from the Crowell and Luvar Chemical Process Safety Fundamentals textbook shows an example data set for temperature versus time and pressure versus time when running in thermal scan mode. And in particular, this data set comes from a methanol and acetic anhydride reaction carried out in an automatic pressure tracking adiabatic calorimeter. In thermal scan mode, the sample is first heated at a constant temperature rate until the reaction rate becomes large enough such that adequate energy is produced for the calorimeter to detect the reaction self-heating. So that detection is shown right here. The calorimeter then switches into adiabatic mode by matching the external and sample temperatures. Once the reactants are consumed and the reaction terminates, shown here, we see the temperature plateaus and the run is ended and the contents in the calorimeter are cooled off. The other mode of operation is called heat weight search mode. And again, we see some sample temperature versus time and pressure versus time data published in the Crowell and Luvar Chemical Process Safety Fundamentals textbook. And this data is for the thermal decomposition of diterbutyl peroxide, also in an automatic pressure tracking adiabatic calorimeter. So for heat weight search mode, when the calorimeter starts heating the reaction mixture, we have heating steps to a fixed temperature, followed by waiting for a fixed amount of time. We're waiting to see if a reaction exotherm is detected. And this is particularly useful if you have reactions that have long induction times. And there might be multiple, or most likely be multiple heat weight search cycles that are necessary until a reaction self-heating is detected. So here we see, as this cycle is done, we see now that we are detecting self-heating. And so again, like now, for the thermal scan mode, the calorimeter switches into adiabatic mode, where the external temperature is maintained, or is attempted to be maintained at the reaction sample temperature. And again, this is important to mimic adiabatic conditions so that you don't have any heat being transferred to or from the reaction sample. Again, once the reactants are consumed and the reaction is finished, more heat weight search cycles can be done to see if there are any other reactions. Once those are completed, again, at the end of the run, the contents are cooled off. As previously mentioned, for adiabatic calorimeters, in order to achieve adiabatic conditions, we want to limit the amount of heat absorbed by the sample cell walls. The thermal inertia of an apparatus, or the phi factor, is defined as the combined heat capacity of the sample and the container divided by the heat capacity of the sample. And that can be rearranged to be 1 plus the heat capacity of the container divided by the heat capacity of the sample. A phi factor approaching 1 represents less thermal inertia. And for large reactors, phi is approximately equal to 1.1. For the types of calorimeters presented in the Crowell-Navarre textbook, the phi factors range from 1.05 to 1.5. In this series of lessons, you are learning about how to characterize chemical reactions using calorimetry. In the next video, we're going to look at analyzing calorimetry data. In this series of lessons, we are working on characterizing chemical reactions using calorimetry. In this particular lesson, we're going to work on analyzing calorimetry data. In the following video, I'll show you an example that demonstrates an application of what we learned here. In the previous lesson, you were introduced to the adiabatic calorimeter. We saw that the data we obtained from calorimetry studies includes temperature versus time data and pressure versus time data. And we can answer some of the questions directly from this data set, including the maximum temperature increase due to adiabatic self-heating and the maximum pressure during the reaction. But we'd like to tease out some more information from this data set, like the maximum rate for self-heating and also the kinetic parameters that describe this reaction. And for that, we're going to need to be able to fit a model to this data set. The model for our calorimetry data will be a mass balance. A mass balance relates the rate of change in the concentration of material to material entering a system minus the amount of material leaving a system plus generation of that material minus consumption of that material in the system. This is the expression for the dimensionless mass balance on the limiting reactant or reactants in our system. And we'll go through variable by variable to understand what each of these terms mean. So first, let's start with this capital X. Capital X is the conversion of our limiting reactant or reactants. So conversion is defined as the moles of the reactant that's reacted over the moles fed. With respect to concentration, the conversion at time point t is equal to the initial concentration of the reactant minus the concentration of the reactant at time t divided by the initial concentration of the reactant. Now again, our calorimetry data is temperature versus time. And if we can relate conversion directly to the temperature, we can express the conversion, again as a function of time, as the current temperature at time t minus the initial reaction temperature, T sub 0, also called the detected onset temperature, divided by the adiabatic temperature change, which is the final reaction temperature when the reaction is completed, minus the reaction onset temperature. The next variable we see in our dimensionless mass balance is tau. Tau is a dimensionless time term. So time is made dimensionless by multiplying it by the K. K is the rate constant at the onset temperature, multiplied by the initial concentration of the reactant to the n minus 1 power, where n is the overall reaction order. Another dimensionless term is this capital B. Capital B is the dimensionless adiabatic temperature increase. So this is information that we can pull directly out from our temperature versus time data set. So B is equal to the final reaction temperature minus the reaction onset temperature, which we saw when we defined conversion as the temperature, the adiabatic temperature change, and that's divided by the onset temperature. Another dimensionless term in this mass balance is sigma. Sigma is the dimensionless activation energy. The activation energy, E sub A, is made dimensionless by dividing it by R, which is the gas constant, times the onset temperature. Finally, N, as was previously mentioned, is the overall reaction order. So those are the variables in this dimensionless mass balance, but you may be wondering, where did this dimensionless mass balance come from? So although I won't step through all the details of the derivation, the building blocks for this mass balance first is the chemical equation. So we have reactants that become products, and each of the chemicals involved in this reaction, so in this case we have reactants A and B, and we could have more, and that makes products, carry a stoichiometric coefficient. So for instance, alpha is the stoichiometric coefficient for A, beta the stoichiometric coefficient for B, etc. So we have the chemical equation, and we can derive a material balance for each component involved in this reaction. So for example, for chemical A, we could prescribe a material balance where the rate of change of chemical A with respect to time, or should I say chemical A, so the concentration of chemical A with respect to time is equal to negative, because it's a reactant, we're consuming it. We have a rate constant K, which is a function of temperature. We have a concentration term for each of our reactants, and this exponent A for the Ca term and B, these would be the order of the reaction with respect to each of these different chemicals. The rate constant, this K of T as a function of temperature, can be expressed using the Arrhenius equation, where K sub 0 is a pre-exponential constant, and again we have E sub A as the activation energy, R as the gas constant, is T as the temperature. We could prescribe the rate constant using a reference condition, for example, the rate constant at the onset temperature, and we see the expression for the rate constant in terms of the rate constant at the onset temperature, and again this E sub A over R term, where we're multiplying it by 1 over the temperature, minus 1 divided by that reference temperature, which in our case is the onset temperature. So these are the building blocks that when put together, we can, in dimensionalizing terms, we could arrive at for our limiting reactant, this dimensionless version of the mass balance that we see here. Before moving forward, we should also understand the assumptions that we make when moving from those building blocks to this expression of the dimensionless mass balance. The assumptions are that the reaction occurs in a closed, well-mixed vessel, that there is either a stoichiometric ratio of reactants, or all but one reactant is fed in excess. So what this means is, again, if we have our chemical equation where reactants equal products, and we have stoichiometric coefficients tied to each of the reactants and products, a stoichiometric ratio, for instance, looking at the ratio of the concentration of reactant B with respect to reactant A, would be the ratio of the stoichiometric coefficients beta to alpha. And the idea of what we want to do here is we want to collapse all these concentrations that are specific to each of the components into one concentration. We're also assuming that there are constant physical properties like the heat capacity and heat of reaction. In order to convert the temperature data into conversion, we are assuming that the heat released by the reaction is proportional to the conversion, and that the conversion is directly proportional to the temperature increase during the reaction. Before moving on to how we can use this model to extract the information we want from our calorimetry data set, let's visualize this model for particular values of these dimensionless parameters. Those parameters being in particular B, which again is the dimensionless adiabatic temperature increase, and sigma, which is the dimensionless activation energy. So just to first orient ourselves to this plot, we see a plot of dimensionless time versus the reaction conversion. And our constraint on the conversion is that it must be between 0 and 1. So 0 would mean that none of our reactant has been converted to products, and 1 would be complete conversion. So all of our reactant has been converted to products. There's no such constraint on dimensionless time, but here we're cutting it off at 1, although we could continue on in this dimensionless time tau as we've defined it. So this particular visual is for a first order reaction, n equals 1, for sigma equals 4, and we're looking at various values of B. So this first trend shows B equal to 0.1. Again, remember that B is the final reaction temperature minus the onset temperature, so that difference is the change, the adiabatic temperature change. And this is, again, divided by the onset temperature. So here we see first B equals 0.1. The orange line is for B equals 0.5. The green trend is for B equals 1. And the blue trend is for B equals 5. So what we see here is that as B increases to higher values, we see that the reaction occurs over shorter and shorter time periods with a much steeper slope. So for example, in this time period for B equals 0.1, we see that at tau equals 1 that we have not yet achieved complete conversion, whereas for B equals 5, we very quickly achieve complete conversion before we reach a dimensionless time point of 0.3. We can also visualize this model for varying values of sigma. So this is a representation of the model results, again, for first order reaction when B equals 1, and for variable sigmas, where again, sigma being the dimensionless activation energy is the activation energy divided by R, the gas constant, and the onset temperature. And so here we see the model results over dimensionless time from 0 to 1 for sigma equals 1, sigma equals 4, sigma equals 8, and sigma equals 15. And again, we see the same relationship or the trend for increasing sigma as we did for increasing B, in that as sigma increases, so the dimensionless activation energy increases, the reaction occurs over shorter time periods and with much steeper slope. So again, we see here for sigma equals 15, we achieve complete conversions, x equals 1, right about at tau equals 0.2. For sigma equals 8, we achieve complete conversion when tau equals 0.3. And for sigma equals 4, we hit that point right about at tau equals 1. One way we can use this model is to determine the maximum self-heat rate. We can find the conversion, so again, X's conversion, at the max self-heat rate by differentiating our mass balance. So again, we have the rate of change of the conversion with respect to dimensionless time. If we differentiate that with respect to dimensionless time again, and set the result equal to 0 to find the max, after a bunch of algebra, we can solve for the conversion at the max self-heat rate. And it's going to be equal to a term that involves all these variables that we defined so far, like the reaction order and the dimensionless adiabatic temperature increase and the dimensionless activation energy. To get a visual on how that expression that we just saw for xm, the conversion at the max self-heat rate, varies with dimensionless adiabatic temperature rise and the dimensionless activation energy, we can visualize this in a couple different ways. And so here we see for a few different sigmas, so we have sigma equals 1, sigma equals 5 in orange, sigma equals 10 in green, sigma equals 30 in blue, and sigma equals 60. We see that as sigma increases, we reach higher and higher conversions for the max self-heat rate. But interestingly too, we also see that there is a maximum there's a max for x sub m as a function of b. So for instance, if we were to look at the sigma equals 30 curve, we see, right about here, right, we reach the peak xm value before we start to trend slightly down. And we can see that max point for each of these xm versus b curves at a given sigma. So if we wanted to figure out where that point was, we could differentiate that xm expression with respect to b instead of equal to 0, and we could do that math. But for here, the takeaway is we see that there is a maximum here, and we see that as sigma increases, we have a higher and higher conversion at the max self-heat rate. We're going to visualize this result one more time with respect to now the dimensionless activation energy sigma. So again, this is still xm on the y-axis and sigma on the x-axis. Here, these lines represent variable values of b. And so we have b equals 0.1 in dark blue, b equals 0.5 in orange, b equals 1 in green, b equals 5 in blue, and b equals 10 in purple. So this looks kind of like a mess. There's not a clear trend here, but this confirms or is another visualization what we saw on the previous slide, because we see as b increases, we see the value of xm start to go down. So after we reach b equals 1, right, we go to b equals 5 at a constant sigma, right, we see that from b equals 0.1, so about here, to 0.5, about here, to 1, we see xm going up. But now when we get to b5, b10, so b5 is about here as well, b10, we see that xm starts to go down again. So we can see again that max value of xm with respect to the parameter b. So that's a lot of information about the model. So let's get back to the data and how we can use the model to tease out some more information from this data set. So here we're looking again at the temperature versus time data from a calorimetry experiment run in the thermal scan mode. And again, there is information that we want that we pull out of this, like the onset temperature and the final temperature. So we get the delta T with TF right here and the onset temperature T0. We have enough information to get the parameter B in our model. But where does the parameter sigma come from, which relates to the activation energy, and so on? So the challenge here is that this temperature versus time data is nonlinear, and it's challenging to fit a nonlinear data set. So what we'd like to do is linearize this data set in order to pull out parameters like sigma, as well as the rate constant at the onset temperature. So let's walk through how to linearize this data set and how the dimensionless mass balance that we've seen can be used to pull out these kinetic parameters from our data set. So our starting point here will be the dimensionless mass balance, and as a reminder, the dimensionless time tau is equal to the rate constant K at the onset temperature T sub 0 times the initial concentration C sub 0 raised to the n reaction order minus 1 times time. So we're going to go through a number of manipulations, and my goal here is for you to understand how this model can be dimensionalized again, so we recover temperature and time, and how we can manipulate that data set to be in the form of a straight line. So the first manipulation we're going to do is we are going to move this 1 minus x to the n term, which was right here, over to the left-hand side of the equation where we see conversion. And we're also going to plug in tau, so we're going to bring in dimensional time back into our expression. So here is tau worked back in. The next manipulation is going to be to take the reaction rate constant term and the associated concentration term, and we are going to move that over to the right-hand side of the equation. So we're just moving that up to the top of the page, so nothing new here. And the next step is we want to get rid of this exponential term, so we're going to go ahead and take the natural log of both sides of the equation. And so using natural log rules, we're able to take the natural log of our rate constant at the onset temperature times the concentration term and add on the argument to the exponential function that we saw before up here. So again, we're just moving this to the top of the page. This is where we left off. Now we want to bring temperature back into this expression. So temperature is hiding here in the conversion as well as in B. So just as a reminder, conversion, because we can, or assuming we can relate the temperature, is equal to the current temperature minus the onset temperature divided by the final temperature minus the onset temperature, T0. B is also related to temperature. Remember, it was delta T, so TF minus T0 over T0. And this combined term of B times X over 1 plus Bx, that is this term right here. When we sub in these temperatures, we get this expression, the current temperature T minus the onset temperature T0 divided by the current temperature T. So plugging in for X and plugging in for Bx over 1 plus Bx, we now have a really messy looking equation. We're working towards what we want, but here, what we have is our mass balance. It's still our mass balance, just we've done some manipulation. And again, now we see our temperatures. So this is all, again, information that relates more directly back to our data set. And we see time over here. So one final time, just moving where we left off to the top of the page, we actually here have our linearized relationship where we have a y equals mx plus b. And that might be a little hard to see. So for illustration, let's look at the case where our reaction order n equals 1. So when n equals 1, this term actually is just 1. So that kind of, is just multiplied by tf minus t to the first power. So that becomes a lot simpler. Same thing over here. When this concentration, or when n is 1, this concentration term is just 1. And so this more maybe directly or more simply shows that we have a y equals intercept plus slope times x. And so if you're familiar with the equation of a line, that is the function for the equation of a line. And so what that tells us is if we take our temperature versus time data and manipulate it to have this set of terms on the y-axis, and on the x-axis have this t minus t0 over t, then what we'd expect to see is a line, and the slope of that line would be equal to sigma, and the intercept of that line is the natural log of the rate constant at the onset temperature. So when we get into our next lesson, we will apply this. We will show how we can use this in order to actually treat a real set of data. So in conclusion, there are a number of results we get from calorimetry studies, all from a single experiment. Just to outline them really quick, they are the max temperature and pressure, the maximum temperature and pressure rates, the adiabatic temperature rise, the heat of reaction, the maximum rate of heat release, the reaction order and rate, the reaction onset and final temperatures, and the time to the maximum rate. Again, some of these come directly from just looking at the temperature versus time and pressure versus time data sets, things like the max and the max rates and the adiabatic temperature rise and the onset and final temperatures. But others, like the rate of heat release and the reaction order and the time at the maximum rate, can be derived from fitting the data to the mass balance that we saw. And so to this point, you've seen the model and you've seen the data. And in the next video, we're going to look at an example of actually determining some of these results by doing the model fit. In the last few videos, we looked at how we can characterize chemical reactions using calorimetry. In this video, we focused on analyzing calorimetry data. In our next video, we're going to apply what we learned in this video by looking at an example. In this series of lessons, we've been working on characterizing chemical reactions using calorimetry. In this lesson, we're going to continue to look at analyzing calorimetry data by doing an example together. For our example, we are going to take the results of a calorimetric analysis of a reactive system where there is a detected onset temperature at 350 Kelvin and a final temperature detected at 450 Kelvin. We're going to assume that we have a reaction order of 1. Taking the assumed temperature versus time data and linearizing it by plotting the natural log of the temperature d time divided by the final temperature minus the current temperature versus on the x-axis temperature minus the onset temperature divided by t, we have what we'd assume to be a straight line with a slope of 30 and an intercept of -10. The R-square fit demonstrate to us that this linearization worked out the way that it was supposed to, and that we can take these results for the slope and intercept and map them to our kinetic parameters. So given this information, this starting point, so this describes this temperature versus time data that we should have and the results of linearizing it, the questions that we're going to answer are: what is the value of B, which is the dimensionless adiabatic temperature rise? What is the value of the dimensionless parameter sigma, which is our dimensionless activation energy? What is the value of the rate constant at the detected onset temperature? What is the activation energy and the pre-exponential factor in our Arrhenius expression for the rate constant? And at what temperature does the maximum self-heat rate occur? So approaching these questions one by one, the first question was, what was the value of B, the dimensionless adiabatic temperature rise? So within the problem statement, from our temperature versus time data that we assume to have, we're told that the final temperature was detected at 450 Kelvin and the onset temperature was detected at 350 Kelvin. Given that the definition of B, the adiabatic temperature rise, is Tf minus T0 divided by T0, we can pretty easily plug in these numbers for the final and onset temperatures and calculate B to be 0.2857. The next item that we were asked is, what was the value of the dimensionless parameter sigma, which is the dimensionless activation energy? So recalling that when we linearize calorimetry data, which is our temperature versus time data, and the linearization is done by taking the natural log of d temperature, d time, over the final temperature minus the current temperature, that would be our y variable, and our x variable would be the temperature minus T0 over the temperature. With that linearization, we would have a intercept, if we find that we have a linear relationship, which we're told in the example that we have via the r squared, the goodness of fit value, we have a intercept that is equivalent to the natural log of the rate constant at the onset temperature and a slope that is equal to sigma. So here, if we realize from the given information in the problem that the linear correlation here had an intercept of -10 and a slope of 30, we know that sigma, the dimensionless activation energy, which is equal to the slope, would be equal to 30. The next question we were asked to answer was, what was the value of the rate constant at the detected onset temperature? So again, here we see that the intercept, which we're told is -10 when we linearize the data, that's equal to the natural log of the rate constant at the onset temperature. So we know then that k at t0 is equal to the exponential function raised to the intercept. So e to the -10 would be equal to 4.54 times 10 to the -5th inverse seconds, assuming that time here is measured in seconds. The next question we're asked is, what is the activation energy in kilojoules per mole and the pre-exponential factor? So we're looking at the parameters for the Arrhenius expression for our rate constant. So again, here we are given in the problem the detected final temperature and the onset temperature. And we know the value of this dimensionless parameter sigma, the dimensionless activation energy, is EA, the activation energy, divided by R, the gas constant, and the onset temperature. So we can calculate the activation energy by multiplying sigma by R and the units that we needed to get EA in kilojoules per mole and the onset temperature. So you have 30 times an expression for the gas constant, 0.008314 kilojoules per mole Kelvin, and the onset temperature, 350 Kelvin. We get the activation energy as equal to 87.3 kilojoules per mole. The Arrhenius expression for the rate constant, K, is the pre-exponential constant times the exponential function raised to the negative EA over RT. So here we can evaluate this at the temperature T sub 0, the onset temperature, because we know the onset temperature, and we also know the rate constant at the onset temperature. That was taken from the intercept of the linear fit that we saw on the previous slide. So we can solve for A being equivalent to the rate constant at the onset temperature divided by the exponential function raised to the negative EA over RT0. Now again, this collection of terms that again is just sigma, so we can take the derived rate constant which came from the intercept and the sigma, which came from the slope, and we can express the pre-exponential factor A as 4.85 times 10 to the 8th inverse seconds. The final question that we're asked for this example is the temperature at which the maximum self-heat rate occurs. So the tool we've seen related to this is the conversion x at which the maximum self-heat rate occurs. And when this was solved, when we derived this, when we looked at analyzing calorimetry data, this is the expression that we had. So 1 divided by 2 times n, the reaction order, times the dimensionless parameter b, times altogether negative sigma plus 2n plus the square root of sigma times sigma plus 4 times n, the reaction order, times the term 1 plus b. So in order to do this calculation, we need n, which we're told the reaction order is 1. We need b, which we've calculated, and we need sigma, which we've also derived from the linear fit. So we can plug this all in. So we see again here 1 for n, and we see b 2.86, we see sigma 30, and so we see other entries for that as well. And you can calculate that the conversion at the maximum rate of self-heat is 0.8211. So how do we relate this to the temperature at which the maximum self-heat rate occurs? Well, we can do that by taking conversion and relating it to how we defined conversion relative to the temperature. So we made the assumption that we could relate conversion to temperature being T minus the onset temperature divided by the range of temperatures, the final minus the onset. So here the T that would be here would be the temperature at which we see the maximum rate of self-heat, because we have the conversion here at the maximum rate of self-heating. And so plugging in for our TF and our T sub 0 and the conversion, we can solve for this temperature at the maximum self-heat rate, and we get the solution that occurs at a temperature of 432 Kelvin. So hopefully in this example you can better understand how to pull out some of these key parameters and these rate constants and kinetic parameters from calorimetry data. Of course, it would have been awesome to start from an actual data set, and those are hard to find and to play around with, but from just looking at the steps and starting from this point where we had a linear fit and a slope and an intercept, we can see how we can then relate these to things like our activation energy, our pre-exponential constant, the conversion at the maximum self-heat rate, and also here this final calculation for the temperature at the maximum rate of self-heat. During the last number of lessons, we've been working on characterizing chemical reactions using calorimetry. Specifically, we discussed the key results that are needed from these experiments, how lab-scale results can be representative of large commercial reactors, how to obtain calorimetry data, and how to analyze calorimetry data. Welcome to this next module, where we'll take a deeper dive into the reactive chemical hazards. Sorry, can I restart that? Welcome to this next module, where we will take a deeper dive into reactive chemical hazards and how to characterize them. We saw at the beginning of this course the powerful explosion and subsequent damage that occurred at and around T2 laboratories in Jacksonville, Florida, due to a runaway reaction. We can expect there to be chemical reactive hazards present where chemistry is designed to take place. But those hazards can also be present in places and processes where chemical reactions are not expected to take place. In this module, you'll reflect on an incident that occurred in 2018 at the TPC Group chemical plant in Port Neches, Texas, where butadiene, a self-reactive chemical, formed popcorn polymer in a process dead leg, or an area of piping that was exposed to the process but rarely saw flow. This reaction yielded an overpressurization event in the piping, which caused its rupture and the release of butadiene. The released butadiene formed a vapor cloud that eventually found an ignition source, resulting in a large fire and explosion. As you begin this module, you will learn about processes and situations where reactive chemical hazards are likely to be present, as well as what specific reactive chemicals are. Next, you will learn how to use a tool called the Chemical Reactivity Worksheet, developed in part by the American Institute of Chemical Engineers for the identification of chemical compatibility and reactive chemical hazards. You will then have an opportunity to apply this worksheet to the TPC Group chemical plant incident. Finally, you will learn how to characterize chemical reactions using calorimetry, including data obtained from calorimetry studies, how to analyze that data, and what important results are gained from these studies. Let's get into it. Hello and welcome to this last module, where we will learn about pressure relief. One of the most important potential consequences of unexpected chemical reactions is the heat produced. This could then lead to the vaporization of the materials in the system, leading to a large increase in pressure. If the vessel containing these materials cannot withstand the higher pressure, the vessel will rupture, leading to the release of potentially toxic and flammable chemicals. We saw an example of this at the beginning of this course during the T2 laboratories incident. The heat generated during the runaway reaction vaporized the materials in the reactor, leading to an overpressurization event. The reactor did have a rupture disk, a type of pressure relief device, but it was not adequate to relieve the buildup of pressure in the system. As you know, the reactor failed and the explosion was devastating. There are many scenarios that could result in equipment being exposed to pressures that they weren't designed to handle. In addition to runaway reactions, these could include out-of-control heating or cooling, valves left open or closed, process upsets, or operator errors, to name some examples. Pressure relief systems discharge liquids or indoor gases before damaging pressures develop. These could be both high pressures as well as low pressures due to vacuum. In the United States, any vessel that's defined as a pressure vessel, which is a vessel with a pressure rating of greater than 15 psi gauge, is legally required to have a relief device. You may have some of these in your home, like a hot water heater or a pressure cooker. Vessels can be designed to operate within desired pressure ranges based on their wall thickness. You may ask, why not just design all vessels sufficiently thick as to withstand very high pressures? Well, the greater the wall thickness, the much greater the cost of the vessel. This economic constraint needs to be balanced with designing the vessel and associated pressure relief system for safe operation. In this module, you'll learn about major classes of pressure relief devices and key terms related to the design and operation of pressure vessels and associated relief systems. You'll learn about options for handling relief effluent and the general process for designing relief systems. We have so much to cover. Let's get started. Congratulations! You have completed this course on chemical hazards with a focus on toxicology and chemical reactivity. You have learned about chemical hazards and how the globally harmonized system can be used as a common language for communicating about these hazards. You've learned about chemical exposure limits and how to quantify the impact of chemical exposure on a population using dose versus response curves. You have also learned about where chemical reactivity hazards are likely to be present and how to characterize chemical reactions using calorimetry. Importantly, you also learn how to manage these hazards, including ventilation systems and PPE when considering toxic chemical hazards, and pressure relief when considering overpressure scenarios, which could be due to a chemical reaction. You can now use this knowledge towards the implementation of safer solutions and work practices. I hope you have found these all to be important, practical, value-added skills that you can take away from this course. I also hope that risk and safety will become a bigger and more important part of your decision-making process both at work and at home. There is so much more to learn on this topic of chemical process safety. To learn more, I encourage you to continue in this specialization. The third course in our process safety specialization deals with chemical source and dispersion models. In that course, you will learn how to model simple liquid and gas leaks and how to assess the potential for toxic exposure some distance from the release. You will also learn about prevention and mitigation measures for those releases. The fourth course deals with understanding and preventing fires and explosions. In that course, you'll learn how to make predictions of the presence of flammable atmospheres and how to make calculations for damage due to explosions. You will also learn about procedures for taking vessels into and out of service and other design concepts for preventing fires and explosions. And finally, if you haven't had a chance to take our first course in the specialization, I encourage you to do so to learn more about how to identify, evaluate, assess, and mitigate hazards in the chemical process industry. You'll learn how to identify and evaluate hazards using tools such as HAZOP, or hazard and operability studies, and how to estimate event frequency using probability theory, event trees, and fault trees, and how to assess risk using layer of protection analysis. There are many other opportunities to continue your learning. In addition to the text I referenced early in the course, I also encourage you to check out the Safety and Chemical Engineering, or SASH modules, available through the American Institute of Chemical Engineers through a collaboration between the Center for Chemical Process Safety and various universities. In conclusion, remember that maintaining a safety mindset on the job and at home requires one to be inquisitive. Be curious as to what could go wrong, how bad it could be, and what could or should be done to address risky activities. Be safe, and I hope to see you in future online process safety courses. At the end of this lesson, you are expected to acquire or improve upon the ability to define several key terms related to pressure relief devices. As we move through the definitions of these key terms related to pressure relief devices, we're going to be looking at how the magnitude of these terms compare to each other on a pressure versus time plot. And so the first definition we're going to look at is the operating pressure. The operating pressure is the gauge pressure in a pressure vessel during normal operations. So of course, equipment is designed to withstand a certain range of pressures, and the operating pressure should be well within the range that can be tolerated by that vessel. The relief device is in place to protect against damage to the equipment due to a pressure excursion outside of the range of pressures that the equipment was designed for, and also protect against the subsequent hazardous consequences of the release of the vessel contents. The maximum allowable working pressure, or MAWP, also called the design pressure, is the maximum gauge pressure permissible at the top of a vessel for a designated temperature. As the temperature deviates from the expected operating temperature, the MAWP is expected to decrease, either due to a decrease in vessel wall metal strength when the temperature goes up, or due to embrittlement when the temperature goes down. Now, the MAWP is not the point at which the vessel fails. Typically, vessel failures occur at about 4 to 5 times of the MAWP, but vessel deformation may occur much sooner than that. The operating pressure, right, is usually no more than 90% of the MAWP for a given vessel. Now turning our attention to the relief device, the set pressure is the inlet gauge pressure at which the pressure relief device begins to open under service conditions. Looking at an example pressure excursion event, we see a case here where the pressure exceeds the set pressure, leading to the pressure relief device beginning to open. And also, as the pressure is being relieved from the system, the pressure exceeds the maximum allowable working pressure. So the difference between the set pressure and the peak we see here on this pressure versus time curve is called the overpressure. The overpressure is the pressure increase in a vessel over the set pressure during the relieving process, and it's typically expressed as a percentage of the set pressure. The overpressure is usually a design specification for a relief device, and it depends on the pressure capability of the protected equipment. Looking now at this difference between the peak in this pressure versus time curve during this example pressure excursion event and the maximum allowable working pressure, we have the accumulation. So the accumulation is the pressure increase in the vessel over the MAWP during the relief process, and typically the accumulation is also expressed as a percentage of the MAWP. Finally, looking at the latter part of this curve, where we see the pressure is relieved from the system and the pressure as time goes on drops back below the MAWP and below the set pressure to the reseat pressure where the valve is reseated, we can define the blowdown as the pressure difference between the relief set pressure and the relief reseating pressure. In this lesson, we looked at a number of definitions for key terms related to pressure relief devices. In our next lesson, we're going to look at different types of relief devices. At the end of this lesson, you are expected to acquire or improve upon the ability to identify and describe major classes of relief devices. The first type of relief device that we're going to look at is the conventional spring-operated valve. The main components of the valve are the valve seat, shown here in pink, the valve plug, shown here in yellow, and the tension spring. The valve plug, here again in yellow, at the bottom of the tension spring is pressed against the valve seat by the tension in the spring, which keeps the valve closed. The spring tension can be used to modify the valve's set pressure. On the process side, when the pressure increases and reaches the set pressure, the pressure at the bottom of the plug becomes greater than the pressure exerted on the seat by the plug due to the tension in the spring, and the valve begins to open and fluid is discharged through the valve. Once pressure is relieved into the system due to the discharge through the valve, recall that the valve will reseat at a pressure that's different than the set pressure, and this is called blowdown. The blowdown is a function of the type of fluid that flows through the relief device, whether it be a liquid or a gas or a vapor. These conventional spring-operated valves are considered to be reliable and versatile. However, there are some disadvantages. The relieving pressure is affected by the back pressure on the valve, and this effectively changes the valve's set pressure. And if this is a significant change, this could result in a hazardous situation. Also, if the built-up back pressure is too high, the valve is susceptible to chatter, which is the rapid opening and closing of the valve. The vibration of the valve could cause valve misalignment and also damage to the valve seat, and also potentially other valve and associated equipment failures. Another configuration of a spring-operated relief device is balanced bellows. Balanced bellows works to reduce the effect of back pressure on the set pressure. And this is done because of the bellows that you can see here on the back side of the valve plug. And this reduces the effect of back pressure on the set pressure as the set pressure becomes a function of the pressure on the process side and the difference between that and the pressure on the vented side of the bellows on the valve plug. These bellows also work to protect the valve spring against exposure to process fluids, which reduce the effects of corrosion on the valve spring. Even though the bellows work to reduce the effect of back pressure on the set pressure, the back pressure in the system still does work against the flow through the valve, so it effectively reduces the flow through the valve. The balanced bellows configuration has its own sets of disadvantages. The bellows themselves are susceptible to fatigue or rupture, and this requires a separate venting system. Another type of relief device is the piston-type pilot-operated safety relief valve. Some of the key components to point out here: first, in yellow, we see the piston, see the valve seat here, with red being the process fluid. We see the pilot valve and the valve dome, and red indicates our process stream here. So we see the same pressure right on the process side and on the dome side of the piston. And due to cross-sectional area differences, when the pressure on the process side exceeds the set pressure, the piston can be drawn back, allowing for the process fluid to be relieved through the valve. So that's our pilot-operated safety relief valve. Again, different than the spring-type valves that we saw before. And some particular advantages of this piston-type pilot-operated safety relief valve is that the relieving pressure is not affected by the back pressure, and you can operate on the process side to a very high percentage of the valve set pressure. These sorts of valves are also less susceptible to chatter than the spring-operated valves. On the disadvantages side, the pilot, as we can see up over here, is susceptible to plugging, and there's also a limited amount of chemicals and temperature conditions that can be used due to these O-rings, these piston seals over here, that would limit, again, what this can be exposed to. The last type of relief device that we're going to look at are rupture discs. Rupture discs we saw earlier in the course in the context of the T2 Laboratories incident. And a rupture disc is a thin diaphragm, usually a solid metal disc, that's designed to rupture at a designated pressure. So in the T2 Labs incident, we saw that the disc ruptured, venting hydrogen to the atmosphere. And these rupture discs can protect against both excessive positive and negative pressures, and they're usually used as the primary relief device when you can have rapid increases in pressure, like in a runaway reaction as happened in the T2 Labs incident, or when you need a large relief vent area. Here's an image of a rupture disc that I took. Let's clear that for a second, and some of the key things you can see here are the size of the discs. This one is 1.5 inches as far as the area, the diameter there. And you also see the burst pressure, and so we see the burst pressure here is 2.54 bar gauge at 250 degrees Fahrenheit. And so importantly, the burst pressure is correlated with that temperature because the pressure does change with the temperature. And this particular rupture disc was purchased for use in a fermenter. Some downsides to rupture discs is once they burst, they remain open. And that could result in the total discharge of your process materials, or you could then have an avenue for air to enter your system, and this could result in a flammable atmosphere if you have a fuel inside your vessel. Also, these rupture discs could burst and be unnoticed by operators. So these are 4 different types of relief devices. Again, we had the conventional spring-operated valves. We looked at balanced bellows, piston-type pilot-operated relief devices, and rupture discs. So hopefully you now know a little bit more about each of these different types of relief devices. In this video, you learned about major classes of relief devices. We looked at conventional spring-operated valves, balanced bellows, pilot-operated relief valves, and rupture discs. Up next, you'll learn about handling relief effluent. At the end of this lesson, you are expected to acquire or improve upon your ability to define and describe options for handling relief effluent. One option for handling relief effluent that we've seen in a previous lesson is a flare. The purpose of a flare is to burn off combustible or toxic gases to produce products that are neither toxic or combustible. One important consideration in designing a flare is the heat intensity at the bottom of the flare stack. And this is something that we considered as an example when we were looking at thermal radiation hazards earlier in this course. Another option for handling relief effluent that could occur upstream of a flare or other process where you don't want liquids to be is a knockout drum, also sometimes called a blowdown drum. So in a knockout drum, a two-phase stream can move into the drum and can be separated into liquid and gas products. So again, if you don't want liquid going to the next downstream process, a knockout drum can be a way to remove that liquid and separate it into its own stream. A horizontal configuration is typically appropriate for use in a relief effluent system, but another configuration could be a vertical configuration here, especially when we have a flare gas stream where we have just a very small amount of liquid. And those droplets can be captured using another liquid such as water. And the gas stream can be harnessed and sent either to the flare or the next subsequent unit operation, whereas the liquid stream can be drained out of the knockout drum. Another unit operation that can occur downstream of a knockout drum is a scrubber. In a scrubber system, you can clean up a contaminated gas stream, like contaminated with a toxic or flammable vapor, using a scrubbing liquid. And so here we see the contaminated gas stream enter at the bottom of the column where it can rise up and interact with this scrubbing liquid that comes in the top and falls down the column. And that interaction could occur over plates or a packed column. And the clean gas is collected at the top of the column after it rises up the column, and the contaminated material is recovered using the scrubbing liquid, and that clean gas can then be sent to vent or to the next unit operation. And the scrubbing liquid needs to be regenerated, so there's another separation here where the chemicals that we're recovering are removed, and the regenerated scrubbing liquid returns to the column to then interact with the contaminated gas. Another potentially economically attractive option is a condenser, when either valuable or hazardous components from a gas stream can be condensed. And so here we see the contaminated gas entering a shell and tube heat exchanger on the shell side, and we see here a two-pass shell and tube heat exchanger on the tube side, where the coolant comes in here at the bottom of the exchanger and the tubes. It moves through two passes and is collected at the top of the heat exchanger, and the cleaned gas is recovered at the top of the shell, whereas the liquid condensate is drained out at the bottom of the shell. So here we see a number of options that can be used for handling relief effluent. Now that we've completed this lesson, hopefully you can define and describe a few options for handling relief effluent. Up next, we're going to look at relevant codes and standards related to pressure protection. At the end of this lesson, you are expected to acquire or improve upon your ability to identify key codes and standards related to pressure relief devices, and to describe pressure vessel requirements and safety relief valve characteristics defined by API, the American Petroleum Institute Recommended Practice 521. So there are many codes and standards that are applicable to pressure vessels and pressure relief systems, and we're going to inventory some of the most important ones here. The first are the ASME boiler and pressure vessel codes. ASME stands for the American Society of Mechanical Engineers, and these codes regulate the design and construction of boilers and pressure vessels. Many undergraduate chemical engineering students learn this and utilize these codes for the calculation of wall thicknesses of pressure vessels. A number of other codes are published by API, or the American Petroleum Institute. And API Recommended Practice 520 deals with the sizing, selection, and installation of pressure relieving devices. API Recommended Practice 521 deals with pressure relieving and depressurization systems. We're going to learn a little bit more about this recommended practice in the next slide. API Recommended Practice 526 deals with flange steel pressure relieving valves. API standard 620 deals with the construction and design of large welded low-pressure storage tanks. API standard 650 deals with welded steel tanks for storage. And finally, API standard 2000 deals with venting, atmospheric, and low-pressure storage tanks. Here we're going to look at relief pressure guidelines adapted from API recommended practice 521. And to visualize this, we're going to look at figure 9.3 from the Crowell-Nuvar process safety textbook. So in this figure, note that on the left-hand side, we have requirements of the pressure vessel. And on the left-hand side, we have corresponding typical characteristics for safety relief valves. In the middle, we have pressure expressed as the percentage of the maximum allowable working pressure in gauge units. So for starters, and we're going to look at some of these definitions that we learned earlier on this week in this course, we see that the normal operating pressure in the pressure vessel shouldn't be any higher than 90% of the maximum allowable working pressure. Correspondingly, on the relief valve side, this can be a standard pressure at which to test for leaks, as the valve should not be open under normal operating conditions. Here at 100%, by definition, we have the maximum allowable working pressure, or the design pressure, for our pressure vessel. And correspondingly, we have the set pressure for our pressure relief system for a particular single valve. And as we learned earlier, the valve reseats. So after the valve opens and it goes to be reseated, it will reseat at a lower pressure than the set pressure. And this difference between the reseat pressure and the set pressure is the blowdown. Moving now to the top half of this figure, we recall that during a relief event, the pressure in our pressure vessel will exceed the maximum allowable working pressure, resulting in an overpressure. This figure shows several important maximum pressures that cannot be exceeded as defined by API recommended practice 521. And we'll work our way from the top down. So we first see that the overpressure during the relieving process cannot exceed the maximum allowable working pressure by more than 121% when there is a fire exposure. In the case that we have a vessel that is equipped with supplemental pressure relief devices, that maximum overpressure is 116% of the maximum allowable working pressure. When we have a single relief device, that percentage of the maximum allowable working pressure is 110%. And that's also the limit, 110%, when we have supplemental relief devices. That's the set pressure for fire exposures as a percentage of the MAWP. Finally, for supplemental relief devices, the maximum allowable set pressure for those supplemental valves is 105% of the maximum allowable working pressure. So again, these are some definitions of some important maximum pressures that cannot be exceeded as defined by API recommended practice 521. In this lesson, you learn some key codes and standards that are related to pressure relief devices. We also looked at some more specific pressure vessel requirements and the corresponding safety relief valve characteristics that are defined by API recommended practice 521. Up next, you'll learn about the general relief system design process. At the end of this lesson, you are expected to acquire or improve upon your ability to describe the general process for relief system design. To get started, let's define the 7 steps in the general process for relief system design. They are: identify the worst credible scenario for a particular operation, obtain key properties of relief discharge materials, determine the appropriate type of relief device and related specifications, document the design basis for the relief system, review the design work, inspect the relief system during construction and final installation, and finally, manage the implementation of recommended testing and maintenance procedures. Let's now look at each of these steps in a little more detail. The first step in the general process for relief system design is to identify the worst credible scenario for a particular operation. So before you can identify the worst credible scenario, you need to ask the question, what equipment in the process needs to be protected by a relief device? So you're looking for equipment that can credibly experience an overpressure or vacuum pressure scenario. And so that equipment would include usually reactors, storage tanks, heat exchangers, towers, drums, blocked-in lines. So consider a liquid in a line that's exposed to the sun and heats up, generating vapor, increasing the pressure in the line. Pumps, compressors, and turbines on the discharge side, and steam jackets in case excessive steam pressures build up inside the jacket. Working towards identifying the worst credible scenario, one needs a scenario identification tool. An example of such a tool is HAZOP, or Hazard and Operability Study, which was taught in the first course of the Process Safety Specialization here on Coursera. So an example of that, we'll look at the reactor in the T2 laboratory incident. And for a HAZOP, we want to ask for each guideword deviation pair, what could cause that deviation, what would be the consequence, and what are particular actions to be taken. So if we're looking at a more temperature deviation, which is a quantitative increase in temperature, a cause, which is what actually happened in that incident, could be the failure of the cooling system in the reactor to adequately remove the heat that's generated from the reaction due to a blockage in the cooling water supply. The consequence that could be associated with that cause is the potential for runaway reaction due to the buildup of pressure in the reactor. And some actions that could be taken would be implementing a backup cooling system, quenching the reaction once the critical temperature is reached, and looking at adding some additional pressure relief on the reactor. So again, here's where we could identify some scenarios. Now, the worst case scenario is the one that requires the largest relief area, which for this example, of course, this would be it. But here's, again, an example of a tool we can use to identify scenarios. We can start to look at making calculations for that relief area, and we'll see that a little bit later on in the determine step. The second step in the general process for relief system design is obtain, with obtain standing for obtaining the key properties of relief discharge materials. So in looking to obtain the physical, thermal, and reactive properties and other materials of what's expected to be discharged to the relief, one can use aspects of safety data sheets for the components, where particularly items 2, the hazards that are identified, and 9 through 11, which detail physical and chemical properties, stability and reactivity, and toxicological information, can all be helpful. Additionally, laboratory testing can be used to fill in any gaps on the properties of materials that are otherwise not known. The third step in the general process for relief system design is determine. And here's where things can start to get really complicated. So first, what are we trying to determine? You're trying to determine what the relief capacity is required for the worst case credible scenario. So the worst case credible scenario is the credible scenario that has the largest relief area. You also want to determine what is the behavior of the vessel contents and the discharge fluid during this worst case credible scenario. You want to determine what the set pressure is, the allowable overpressure, and all of those other pressure set points that we defined earlier on in the week. And you want to determine what the appropriate type of relief device is for this application. So would that be a conventional spring-loaded device, balanced bellows, piston-type pilot-operated, rupture disc, etc. So on the previous slide, we said that the worst case credible scenario is the scenario that has the largest relief area. So let's talk a little bit about sizing relief devices. So sizing relief devices involve calculations that are done to determine the area, the vent area of the relief device. And this drawing shows the general correlation between the percent overpressure and the vent area. And this might seem like a really interesting relationship that shows a very significant decrease in the vent area as the overpressure increases. And this is because, if you recall, the purpose of the relief device is to remove energy from the process. And so as this percent overpressure increases, the pressure driving force through the relief device increases, meaning that the energy density of the fluid that's being charged also increases. So these changes together result in a very significant decrease in the required vent area as this percentage overpressure increases. The calculations that are done to size relief devices are very complex. We're really just going to scratch the surface here for one particular application as a demonstration. When looking to size relief devices, experts in this area should be used to guide the process of designing the relief system. We're now going to pretty quickly look at some example equations that can be used for the sizing of relief devices. And the specific example application that we'll look at is two-phase flow during runaway reaction relief using the Leung method. So before we look at what those equations can look like, we need to understand the assumptions that are used in the development of these equations. And those assumptions are that we have an adiabatic process, so there's no temperature control. There's uniform froth or homogeneous vessel venting. There's little variation in the mass flux during the relief process. The mass flux is mass per area per time, and little variation means that we're treating that mass flux as a constant. There's also a number of other things we're going to treat as constant, including the reaction energy per unit mass and the physical properties of the fluid, including the heat capacity and the heat of vaporization. A final assumption is that the system is a tempered reaction system. And that's because there's liquid in the reactor, and that liquid is volatile. It vaporizes during the relieving process. And as that fluid vaporizes, energy is removed due to the heat of vaporization, and that heat removal tempers or balances the rate of temperature rise in the reactor due to the runaway reaction. So these are the assumptions that are built into the equations. Now let's look at what those particular equations are. The first step towards sizing a relief device is to model the mass flux through the relief. The mass flux, which we'll use G as the symbol to describe the mass flux, is the mass per unit area per time. To model the mass flux, we need a source model. A source model describes how materials are discharged from a process. If you'd like to learn more about how to derive simple source models, you should check out the next course in our process safety specialization. For this example, the source model that's appropriate is that for a choked two-phase flow through a hole, where two-phase flow means we have both vapor and liquid, and choked flow is a limiting condition at sonic velocity. The source model derived for this situation shows that the mass flow through the relief in units of mass per time is equal to the heat of vaporization of the fluid in units of energy per mass times the area of the hole in units of length squared, divided by the change in the specific volume of the flashing liquid. Specific volume is in units of volume per mass, and the Fg here stands for liquid, the transition from liquid to gas. You multiply that by this term, it's the square root of G sub C. G sub C is a unit correction factor when going from mass to force. T sub S is the absolute saturation temperature of the fluid at the set pressure, and C sub P is the heat capacity of the fluid in energy per mass per degree. Now we want the mass flux, and so the mass flux, again, G, is the mass flow rate per area. So we just divide by the area, and we have an equation that describes the mass flux. This model for the flux is known as the equilibrium rate model for low-quality choked flow. And this method is called the Leung method because Leung showed that this model needs a correction factor, is 0.9 times psi, to bring the model result for the mass flux. Again, that is G, in line with a classic homogeneous equilibrium model. So this psi factor here its theoretical limit is 1 when the pipe length is equal to 0. So obviously in real life, we have pipe lengths that are not non-zero. And as the pipe length increases, the value of psi decreases. And the correlation for psi with pipe length can be found in Leung's publications. So here we have a model for two-phase flow through pipes that's generally applicable to the homogeneous venting of a reactor. The next step in determining the size of the relief device is to calculate the required vent area. And as you might imagine, we're going to make use of the mass flux that we just saw on the previous slide. The equation for the required vent area comes from the mechanical energy balance. And if you're not familiar with the mechanical energy balance, this defines a conservation of energy in a fluid. It's usually derived between two states, and the mechanical energy balance takes into account the change in pressure energy and kinetic energy and potential energy in the fluid, as well as any work that may have been put into the fluid and any frictional losses in the system. So for this situation, here is the result for the vent area A. And you'll recognize first, here's the mass flux that we need. Again, it's mass per area per time. We see some other terms familiar from the previous slide, like the heat of vaporization and the change in the specific volume of the fluid as it is flashed. And a few other new terms we see are this m sub 0, that is the total mass in the reactor vessel before the relief. We see this term little q, that stands for the exothermic heat release per unit mass, which can be determined from fundamental kinetic information or from a calorimeter. Again, think of what we learned last week in this course. And V is the volume of the vessel. So the purpose here was just to show you some equations. And again, these are very particular for this example system, which is two-phase flow during a runaway reaction relief, specifically using the Leung method. Hopefully you have a little insight, again, to thinking about the flux, the amount that's moving through the relief, and the required relief area, and how this all works out for this particular example. So a final important part of the determine step is thinking about how the effluent needs to be handled. So in a previous lesson, we saw particular unit operations that could be involved in handling relief effluent, including knockout drums, scrubbers, condensers, and flares. And based on the information that was obtained in the obtain stage, right, where you looked at the physical and thermal and reactive properties of the relief discharge material, one needs to make a decision on what combination of unit operations is appropriate. So, for example, could the relief effluent go to a scrubber to scrub out the contaminants such that the clean gas could be vented? Or should it be sent to a knockout drum where then the vapor that is collected can be sent to flare with the liquid being drained, sent to a drain? So again, what's appropriate would be a function of the particular properties of the relief effluent. It would need to be determined. So after that very involved determine step to figure out the appropriate type of relief system and the related specifications and how the effluent is handled, we'll now overview the final steps in the general process for relief system design. So again, those are first, document. So the design basis for the entire relief system, going back to those first few steps, needs to be documented. Then all the design work that has been completed needs to be reviewed. During construction and final installation, the system needs to be inspected. And finally, the recommended testing and maintenance procedures need to be managed to ensure that they're properly implemented. In this lesson, you learned the general process for relief system design. Up next, you're going to look at a case study involving an ethylene release and subsequent fire at Carre America in Texas.